Imagine a universe so huge it holds more stars than grains of sand on Earth. This idea only hints at the mysteries out there. From galaxies being born to planets moving silently, space reveals clues about our origins and the nature of reality. Join us on a journey to explore the universe, challenging what you know and sparking curiosity about the wonders yet to be discovered. The Big Bang Theory is the leading explanation for the origin of our universe, and it is supported by multiple lines of compelling evidence. One of the most striking pieces is the observation of the cosmic microwave background radiation. This faint glow, which fills the universe and can be detected in every direction, is considered the aftershock of the Big Bang itself. It offers a snapshot of the early universe, a hot and dense place that has since expanded and cooled over billions of years. Another significant piece of evidence comes from the redshift of galaxies. When we look into the night sky, we find that most galaxies are moving away from us, and the light they emit shifts towards the red end of the spectrum. This redshift indicates that the universe is expanding. If we rewind this expansion, it suggests that there was a time in the past when all the matter was concentrated in a single, incredibly dense point. This idea aligns perfectly with the Big Bang Theory's initial conditions. Additionally, the abundance of light elements, such as hydrogen and helium, offers further support. According to the Big Bang nucleosynthesis theory, the very first moments of our universe's existence allowed for the creation of these simplest elements in significant quantities. When scientists compare the predicted ratios of these elements to what we observe in the universe today, they find a remarkable match, reinforcing the idea that the universe underwent a hot, dense state at its beginning. Finally, we see the large-scale structure of the universe and how galaxies are distributed the way the Big Bang Theory would predict. The formation of galaxies and clusters, shaped by the gravitational effects of dark matter, aligns with the predictions made from our understanding of cosmic evolution from that initial explosive moment. Together, these pieces of evidence not only support the Big Bang Theory, but they also spark a deep fascination for understanding our cosmic origins and how everything began. Cosmic microwave background radiation, often abbreviated to CMB, is an astonishing remnant of the universe's infancy. This radiation is essentially the afterglow of the Big Bang, existing as a faint glow permeating the cosmos. It provides a snapshot of the universe when it was just about 380,000 years old, a crucial period when temperatures cooled enough for atoms to form and light to travel freely. Upon its release, this radiation spread throughout the universe, carrying with it vital information about the conditions of the early cosmos. The discovery of the CMB unfolded in the early 1960s by Arno Penzias and Robert Wilson, two radio astronomers searching for a source of noise in their measurements. What they stumbled upon was the hallmark of the early universe, a uniform background radiation present in all directions. Their finding corroborated the Big Bang Theory and was pivotal, providing a concrete piece of evidence that the universe had a hot and dense beginning. This helped shift scientific consensus, confirming that the universe was not static, but ever expanding. Since that landmark discovery, astronomers and cosmologists have developed a deeper understanding of the fluctuations within the CMB. These tiny variations represent the seeds of all structure in the universe, such as galaxies and clusters of galaxies. By analyzing these fluctuations, scientists have been able to glean important details about the age, composition, and evolution of our universe. The patterns revealed by the CMB have become cornerstones in cosmology, allowing for precise measurements of the cosmos's expansion rate and the relative proportions of dark matter, dark energy, and ordinary matter. The cosmic microwave background radiation serves as a cosmic echo, telling us about the universe's very first moments. It not only helps us understand the origins of the universe, but also invites us to ponder our place within it. With every new bit of data collected from missions dedicated to studying the CMB, we inch closer to unraveling the mysteries of the cosmos and envisioning what the universe was like when it first began its grand journey. Inflation theory revolutionizes our understanding of the early universe by proposing a period of rapid expansion just moments after the Big Bang. According to this theory, the universe did not expand smoothly, but instead underwent an exponential growth spurt, expanding faster than the speed of light. This brief but intense period of inflation dramatically stretched the universe, smoothing out any irregularities and seeding the large-scale structure we observe today. One critical implication of inflation theory is that it explains why the universe appears so homogeneous and isotropic, meaning it looks the same in all directions. Without inflation, we would expect to see significant variations in temperature and density across the cosmos. Instead, observations from the cosmic microwave background radiation show that, despite local differences, the universe has a remarkably uniform temperature when viewed on large scales. Inflation accounts for this uniformity by stretching out places of higher and lower density, leading to a smoother overall structure. Furthermore, inflation introduces the idea of quantum fluctuations during this rapid expansion. These tiny variations, generated by the uncertainty of quantum mechanics, acted like seeds for later structure formation. As the universe expanded and cooled, these fluctuations grew due to gravitational attraction, eventually leading to the galaxies, clusters, and vast cosmic filaments we observe today. This connection between quantum physics and cosmic structure is a profound insight and alters our perspective on how the universe has evolved over billions of years. Lastly, inflation theory also raises intriguing questions about the very nature of our universe. It suggests there could be other regions of the universe or even other universes existing beyond our observable horizon, leading to the idea of a multiverse. This concept challenges our traditional understanding of reality and encourages further exploration into the fundamental nature of existence and the mechanisms that created our universe. Nucleosynthesis is the process by which elements are formed through nuclear reactions, and it played a crucial role in the development of our universe after the Big Bang. In the first few minutes following this monumental event, the universe was an extremely hot and dense environment, allowing nuclear reactions to occur. During this time, protons and neutrons, the building blocks of atomic nuclei, combined to create the lightest elements, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. This early period of nucleosynthesis is often referred to as Big Bang nucleosynthesis. As the universe expanded and cooled, these light elements began to dominate. Approximately 75% of the ordinary matter in the universe became hydrogen, while about 25% became helium. The light elements formed during this time set the stage for the future development of stars and galaxies, as they would later fuse together under the intense pressure and heat in stellar interiors to create heavier elements. As stars formed from these primordial materials, they engaged in their own nucleosynthesis processes. Within their cores, through fusion reactions, hydrogen was converted into helium, and over time, as stars aged and died, they produced heavier elements like carbon, oxygen, and iron. When massive stars reached the end of their life cycle, they exploded in spectacular supernovae, dispersing these newly formed elements back into space, enriching the interstellar medium. It is this continual cycle of stellar nucleosynthesis and the recycling of elements that has led to the rich variety of chemical elements we observe today in the universe. In this way, nucleosynthesis not only forged the foundational elements of the cosmos, but also set in motion the incredible processes that would eventually lead to planets, life, and our own existence. Dark matter is one of the most intriguing puzzles in modern cosmology. Although it cannot be seen directly and hasn't been detected through electromagnetic radiation, scientists infer its presence from the gravitational effects it has on visible matter, such as galaxies and galaxy clusters. This mysterious substance seems to constitute about 27% of the universe. Indeed, its existence shapes the cosmos but remains hidden, veiled from our direct observation. The influence of dark matter on the structure of the universe is both profound and fundamental. It acts as a sort of scaffolding, guiding the formation of galaxies and large-scale structures. As gravity pulls regular matter together, dark matter provides the necessary mass to prevent these structures from flying apart. Observations reveal that galaxies rotate at speeds that should, according to Newtonian physics, cause them to fling stars outward into space. Yet they remain intact, suggesting that a significant amount of undiscovered mass holds them together. Furthermore, the distribution of dark matter affects how galaxies cluster and form large cosmic structures. Areas of higher dark matter concentration lead to denser regions of visible matter, creating clusters of galaxies. This clustering is essential for understanding how the universe evolved from a hot, dense state shortly after the Big Bang to the complex web of galaxies we see today. Without dark matter, the universe would appear drastically different, with fewer galaxies and a more chaotic arrangement. Despite its significance, dark matter remains elusive. Numerous experiments are ongoing, both on Earth and in space, seeking to capture it directly or understand its properties better. Some speculate that it may consist of yet-to-be-discovered particles, while others explore alternative theories about gravity that could account for the phenomena attributed to dark matter. Every new discovery brings us closer to unveiling the secrets of the universe and understanding our place within it. The life cycle of a star is a fascinating journey that begins in a stellar nursery, where clouds of gas and dust come together under the force of gravity. However, not all stars follow the same path. Their size plays a crucial role in shaping their destiny. For instance, red dwarfs, which are the smallest and dimmest type of star, have a remarkably long lifespan that can span trillions of years. Unlike larger stars, red dwarfs burn their hydrogen fuel slowly and steadily, often remaining stable for eons before eventually evolving into a white dwarf. In contrast, massive stars experience a more explosive life cycle. They burn through their hydrogen reserves at a much faster rate due to their immense gravitational pressure and temperature. This rapid consumption leads to a series of dramatic transformations, including the fusion of increasingly heavier elements. After a brief phase as a supergiant, these stars reach a critical point in their life cycle. When their core becomes predominantly iron, fusion can no longer produce energy, leading to catastrophic collapse. The result is a spectacular supernova explosion, one of the most violent events in the universe. This explosion not only scatters the star's outer layers across space, but also leaves behind a dense remnant, which can become either a neutron star or even a black hole, depending on the initial mass. Such remnants become critical to the universe as they contribute essential materials for the formation of new stars, planets, and potentially life. While red dwarfs and massive stars illustrate extreme ends of the stellar life cycle, the variety of star-like beings in the universe is vast and wondrous. Each type of star, with its unique birth and death phases, showcases the complex processes that govern the cosmos, inviting us to ponder our place within this grand tapestry of existence. The birth of a star is a remarkable journey that begins deep within nebulae, vast clouds of gas and dust scattered across the cosmos. Initially, these materials come together due to gravitational forces. As the gas and dust clump together, regions within the nebula become denser and start to collapse under their own gravity. When this happens, a core forms at the center of the collapsing material, and as it condenses, the temperature begins to rise significantly. As the core continues to accumulate mass, it reaches a crucial point where the pressure and temperature become high enough to trigger nuclear fusion. This transformative event signals the birth of a new star. During the fusion process, hydrogen atoms combine to form helium, releasing an immense amount of energy in the form of light and heat. This marks the star's life cycle's beginning, as it becomes a shining beacon in the dark vastness of space. Simultaneously, while a star is forming, the surrounding material begins to experience dynamic changes. The gravitational pull of the newly formed star influences the orbiting gas and dust, causing it to flatten into a disk shape. This rotating disk is rich in elements and is the critical environment where planetary systems begin to form. Through various processes, tiny particles collide and stick together, growing larger over time to form planetesimals, the building blocks of planets. As these planetesimals continue to collide and merge, they eventually become protoplanets. Over millions of years, these protoplanets evolve into the planets, moons, and other celestial bodies of a solar system. Each stage of this remarkable journey, from the birth of stars to the creation of planets, reflects the intricate dance of gravity, matter, and energy, illustrating the beauty of cosmic evolution. Supernova events represent one of the most spectacular phenomena in the universe, marking the explosive death of massive stars. To understand this process, we must first consider what happens in the core of a star. As a massive star exhausts its nuclear fuel, it can no longer support itself against the force of gravity. In the late stages of its life, the core contracts while the outer layers expand, creating a supergiant star. Once the core becomes predominantly iron, the processes change dramatically. Iron cannot release energy through fusion, leading to the buildup of pressure. Beyond a critical point, the core collapses under its own weight, generating an enormous shock wave. This shock wave travels outward, expelling the outer layers of the star into space at incredible speeds, and this is what we observe as a supernova. The aftermath of a supernova is just as fascinating. The explosion disperses heavy elements like carbon, oxygen, and iron into the cosmos, enriching the interstellar medium. These elements are essential for the formation of new stars, planets, and even life. Each supernova can create beautiful nebulae, which in time will become the cradle for new stars and solar systems. Furthermore, studying supernovae provides critical insights into the universe itself. They serve as indicators of distance and play a key role in understanding the dynamics of cosmic expansion. By observing the light from distant supernovae, astronomers can glean information about the universe's history, its rate of expansion, and the mysterious dark energy. These explosive events are not just endings, but beginnings that weave the fabric of our universe, reminding us of the continuous cycle of creation and destruction. Neutron stars are among the universe's most fascinating celestial objects. They form when a massive star exhausts its nuclear fuel and undergoes a supernova explosion. When this happens, the core of the star collapses under its own gravity, causing protons and electrons to merge into neutrons. The result is an incredibly dense object, composed almost entirely of neutrons, that can pack more mass than the Sun into a sphere only about 20 kilometers across. This compactness means that a sugar cube-sized amount of neutron star material would weigh around 1 billion tons on Earth. These stars possess extraordinary physical properties that make them unique and essential for scientific research. First and foremost, their surface gravity is about 2 billion times stronger than Earth's. This immense gravitational pull creates extreme conditions, allowing physicists to study matter under pressures and densities found nowhere else in the universe. Neutron stars can also rotate very quickly, with some spinning several hundred times per second. This rotation, combined with their strong magnetic fields, gives rise to neutron stars known as pulsars, emitting beams of radiation that can be detected as regular pulsations from Earth. Neutron stars serve as cosmic laboratories for extreme physics in various ways. One of the most exciting aspects is their role in testing theories of gravity. By observing how matter behaves in the intense gravitational field of a neutron star, researchers can investigate general relativity and probe the limits of our understanding of physics. Additionally, scientists study the states of matter in these stars, where conditions may lead to exotic forms of matter that could challenge existing theories. Moreover, neutron stars also amplify the quest to understand the universe's most fundamental forces. When two neutron stars collide, they produce a cataclysmic event, releasing gravitational waves and heavy elements like gold and platinum into the universe. These interactions offer clues about the origins of elements and the nature of gravity, making neutron stars not just objects of curiosity, but key players in our understanding of the cosmos. Black holes are some of the most fascinating and enigmatic objects in the universe. They form from the remnants of massive stars after they have exhausted their nuclear fuel. When a giant star reaches the end of its life, it undergoes a dramatic collapse. The core implodes under its own gravity, while the outer layers can explode in a spectacular supernova. If the core's mass is sufficient, usually more than about 3 times that of our Sun, it compresses into a point of infinite density, known as a singularity, surrounded by an event horizon, the boundary beyond which nothing can escape. Key characteristics of black holes include their mass, spin, and electric charge. The mass of a black hole determines the strength of its gravitational pull, and they can vary greatly in size, from several times that of our Sun to supermassive black holes that can contain millions or even billions of solar masses at the centers of galaxies. The spin refers to how fast the black hole is rotating, which can influence the space around it and create fascinating phenomena such as the formation of accretion disks, spirals of gas and dust that heat up and emit tremendous energy as they are pulled into the black hole. Another impressive feature of black holes is their event horizon. This is a critical boundary, and once something crosses it, it cannot return. The event horizon itself isn't a physical surface, rather it's a point of no return. For an outside observer, as an object approaches a black hole, it appears to slow down due to the extreme gravitational time dilation, a fascinating effect of general relativity. To the observer, the object never seems to actually cross the event horizon, instead appearing to fade away. Despite their mysterious nature, black holes play a crucial role in our understanding of the universe. They offer valuable insights into the laws of physics, particularly in the realms of gravity and quantum mechanics. As we continue to study these cosmic giants, we unravel layers of their secrets, inviting us to explore questions about the very fabric of reality. Black holes, with their deceptive simplicity, hold keys to some of the most profound mysteries of our cosmos. Galaxies are vast collections of stars, gas, dust, and dark matter, and they come in a variety of shapes and sizes. The three primary types of galaxies are spiral, elliptical, and irregular galaxies. Each type has unique features that set them apart, shaping our understanding of the universe and its formation. Spiral galaxies are perhaps the most iconic among the types. They feature a flat, rotating disk filled with stars, gas, and dust, along with a central concentration of stars known as the bulge. Spirals often showcase distinct winding arms that extend from the center, creating a beautiful display of structures. Our own Milky Way is a prime example of a spiral galaxy, demonstrating how these systems can maintain ongoing star formation in their arms. Elliptical galaxies, in contrast, are more rounded and lack the distinct arms seen in their spiral counterparts. They range in shape from nearly spherical to elongated and consist predominantly of older stars, with little to no ongoing star formation. These galaxies often have a smooth, featureless appearance, as the gas and dust needed for new stars has mostly been exhausted. Their formation is generally linked to the merger of smaller galaxies, which can lead to a more homogeneous stellar population. Lastly, we have irregular galaxies. As the name suggests, these galaxies don't fit neatly into the spiral or elliptical categories and often appear chaotic in structure. They are typically rich in gas and dust, which allows for vigorous star formation. Irregular galaxies can result from gravitational interactions or collisions with other galaxies, making them fascinating examples of cosmic dynamism. Each galaxy type tells a part of the grand story of the universe, showcasing the diverse processes that have shaped the cosmos over billions of years. The Milky Way galaxy, once thought of simply as a vast collection of stars, gas, and dust, reveals a more intricate personality with the insight that it possesses a barred spiral structure. This structural characteristic suggests that our galaxy is not static, but instead a dynamic system that evolves over time. The discovery of the bar within our galaxy provides a framework for understanding how galaxies form and change, reshaping our perspective on galactic evolution. Barred spiral galaxies represent a significant phase in the life cycle of many galaxies. The detection of a bar in the Milky Way prompts astronomers to consider how such features influence star formation. The bar's presence channels gas toward the galaxy's center, often leading to vigorous star births as material converges. This understanding helps scientists connect the dots between the structure of a galaxy and its energetic developmental processes, highlighting the interconnectedness of form and function in the cosmos. Furthermore, this revelation encourages researchers to rethink how galaxies interact with their environment. The Milky Way's barred spiral structure may influence its gravitational interactions with neighboring galaxies, shaping how they evolve jointly over time. With this new model, astronomers can better predict how similar galaxies might evolve based on their structural characteristics. As we peer deeper into our galaxy and beyond, recognizing the Milky Way as a barred spiral prompts us to consider the broader implications for the universe. How do these structures affect galaxy formation across the cosmos? Studying the Milky Way will not only illuminate its own history, but also provide essential clues about the life cycles of countless other galaxies, painting a comprehensive picture of the grand tapestry that defines our universe. Galaxies are vast collections of stars, gas, dust, and dark matter, and they do not move through the universe in isolation. They are part of a dynamic cosmic dance, often influenced by their gravitational pulls. When galaxies come close to one another, their mutual gravity can lead to various fascinating interactions. These encounters can be peaceful, leading to subtle changes, or they can instigate dramatic transformations that reshape entire galaxies. One common outcome of these interactions is the phenomenon known as galactic mergers. When two galaxies collide, they can combine to form a larger galaxy. This process can take millions to billions of years, but the result can be quite spectacular, leading to the birth of new stars as gas clouds compress and heat up. Sometimes these mergers create irregular galaxies with new shapes and structures, selling the story of their cosmic past. Not all encounters lead to mergers. Many galaxies pass by each other at great speeds, exerting gravitational forces that can rip stars and gas away from one another. This tidal interaction can also lead to the creation of new structures, such as tidal tails or streams of stars extending from the galaxies. The delicate balance of forces in these encounters can yield beautiful, elongated shapes that speak to the history of the interaction. Further, in dense regions of the universe, such as the centers of galaxy clusters, we often witness even more complex interactions. Galaxies here can collide repeatedly, leading to higher rates of star formation and the stripping away of materials. Each interaction leaves a mark, shaping not only the galaxies involved, but also the overarching cosmic landscape. Through these intricate interactions, galaxies tell the story of the universe's evolution, highlighting how interconnected and dynamic our cosmos truly is. Supermassive black holes hold a pivotal role at the centers of galaxies, acting as both the heart and a powerful influence over the dynamics of their surroundings. Typically, these black holes possess masses that can reach millions or even billions of times the mass of our Sun. Scientists believe that nearly every large galaxy hosts one of these colossal entities, and their presence is integral to understanding the formation and evolution of galaxies themselves. The gravitational pull exerted by supermassive black holes profoundly affects the motion of stars and gas within the galaxy. As objects orbit the black hole, their speeds and trajectories can be influenced in such a way that they behave almost like a cosmic clock, helping astronomers to map the distribution of matter, both visible and dark, within the galaxy. Observations have shown that the dynamics of a galaxy can change when it hosts a supermassive black hole, including the orbits of stars that come perilously close to it. Moreover, supermassive black holes are usually surrounded by a vast accretion disk of gas and dust. As this material spirals inward, it heats up dramatically due to friction and gravitational forces, often emitting intense radiation, including X-rays. This energetic activity can produce powerful jets of particles shooting out from the poles of the black hole, influencing the surrounding interstellar medium and consequently star formation processes in the galaxy. Supermassive black holes are far more than just dark cosmic anchors. They govern the environments around them in a delicate dance of attraction and energy. Their presence shapes not only the structure of their host galaxies, but also the life cycles of stars, ultimately contributing to the complex tapestry of the universe we see today. Galaxy clusters are fundamental to our understanding of the universe's large-scale structure. They are enormous collections of galaxies, gas, and dark matter bound together by gravity. These clusters can contain hundreds or even thousands of galaxies and encompass vast regions spanning millions of light-years. Their sheer size and mass make them key players in the cosmic web, providing valuable insights into how galaxies and structures develop over billions of years. Studying galaxy clusters helps astronomers map out the distribution of matter in the universe. The way these clusters form and evolve is influenced by both visible matter, like stars and gas, and invisible components such as dark matter. Observing the clustering of galaxies allows scientists to infer the presence of this dark matter, which makes up about 25% of the universe's total energy density. The arrangement and dynamics of clusters also cast light on the overall geometry and expansion of the universe, revealing the enigmatic nature of dark energy that composes another 70%. Moreover, galaxy clusters act as laboratories for studying fundamental cosmic processes. The hot gas between galaxies emits X-rays, which can be detected by space telescopes, revealing information about temperature and density. This data can provide insights into cluster formation and the physics governing these vast systems. The merging of clusters can also create shock waves and cosmic phenomena that illuminate the behavior of matter and energy under extreme conditions, offering clues about the fundamental nature of the universe. Galaxy clusters are not merely collections of galaxies. They are pivotal in unraveling the mysteries of cosmos. By studying their formation, distribution, and evolution, scientists gain a clearer picture of the universe's makeup and its history. Through ongoing research on these colossal structures, we deepen our understanding of the forces that shape the universe as a whole. The discovery of exoplanets, or planets outside our solar system, has revolutionized our understanding of the universe. Scientists have employed several clever methods to detect these distant worlds. One of the most common techniques is the transit method, where astronomers observe a star and watch for periodic dips in brightness. These dips occur when an exoplanet passes in front of the star, blocking a fraction of its light. This technique has been extensively used by missions like the Kepler Space Telescope, which has significantly expanded our knowledge of planetary systems. Another method involves the radial velocity technique, which measures the subtle wobbles of a star caused by the gravitational pull of an orbiting planet. As a planet moves around a star, the star itself moves slightly due to the gravitational interaction. By analyzing shifts in the star's light spectrum, scientists can determine the presence of a planet as well as its mass and orbit. This method has been crucial in confirming many discoveries made through transits. Surprisingly, astronomers have uncovered a remarkable diversity in exoplanet types. We have found hot Jupiters, large gas giants that orbit very close to their stars, which defies prior expectations about planet formation. Additionally, the discovery of Earth-sized exoplanets in the habitable zone, an area around a star where conditions could be just right for liquid water, has fueled excitement about the possibility of alien life. One of the most astonishing findings is the sheer number of planets. Estimates suggest there could be billions of Earth-like planets scattered throughout our galaxy alone. These discoveries have sparked questions about the nature of planetary systems and their potential for supporting life. Each new finding challenges our previous assumptions and broadens our horizons. As technology advances and our observational capabilities improve, the quest to understand the universe's exoplanetary landscape continues, revealing more about the cosmos and our place within it. This ongoing exploration reminds us just how much is still out there waiting to be discovered. When we venture into the cosmos, one captivating topic captures the imagination: the search for potentially habitable exoplanets. These distant worlds orbit stars outside our solar system, and scientists have identified several key characteristics that suggest they could support life as we know it. First and foremost, these planets must reside within a star's habitable zone, often referred to as the Goldilocks zone. This is the sweet spot where conditions are just right, not too hot and not too cold, for liquid water to exist on a planet's surface. In addition to being in the right location, potentially habitable exoplanets often have similar sizes to Earth. Scientists believe that rocky planets larger than about a planet the size of Mars, but smaller than a gas giant like Neptune, are more likely to retain an atmosphere capable of supporting life. This atmosphere plays a crucial role in regulating temperature and protecting potential life forms from harmful radiation. The composition of the atmosphere must also be examined. It should ideally include elements like oxygen and carbon dioxide, which are essential for life on Earth. To determine the viability of these exoplanets for life, scientists employ various techniques. One common method is to analyze the starlight passing through a planet's atmosphere during transits, when the planet moves in front of its star. This can reveal the chemical makeup of the atmosphere, helping researchers assess whether it contains the necessary ingredients for life. Moreover, the study of surface temperatures and geological features through advanced techniques like spectroscopy provides clues about each planet's environment and its potential for hosting living organisms. Finally, the field of astrobiology brings together knowledge from various domains, including molecular science, geology, and planetary science, to enrich our understanding of what constitutes a habitable environment. As new telescopes and instruments are developed, the quest for potentially habitable exoplanets continues to expand. Every discovery has the potential to rewrite our understanding of life in the universe, reminding us that we are part of a vast cosmos filled with wonder and possibilities. The search for biosignatures is a pivotal part of understanding the potential for life beyond our planet. A biosignature refers to any substance or phenomenon that provides scientific evidence of past or present life. These could be gases, such as oxygen and methane, which on Earth are primarily produced by biological processes. When we analyze the atmospheres of distant exoplanets, we look for these compounds as indicators that life might exist or might have existed in some form. Detecting biosignatures involves sophisticated techniques and instruments. For instance, telescopes equipped with advanced spectrometers can examine light from distant planets and their atmospheres. By studying how this light is absorbed or emitted, scientists can identify the chemical components present. If we find an atmosphere rich in oxygen and methane, it raises exciting questions about the processes at play. Could there be life forms similar to those on Earth that are actively producing these gases? The search is not limited to distant worlds. Our exploration of Mars and the icy moons of Jupiter and Saturn also focuses on potential biosignatures. Rover missions on Mars seek organic compounds and signs of water, while missions to moons like Europa and Enceladus explore subsurface oceans that may harbor microbial life. Each discovery enhances our understanding of where life could exist in the universe, charting new territories in our quest to find life beyond Earth. Ultimately, the study of biosignatures helps reshape our view of life. It encourages us to think about the diverse forms that life might take and the environments it could inhabit. As we continue to expand our knowledge and refine our technologies, each new finding brings us closer to answering the age-old question of whether we are alone in the universe, igniting both scientific curiosity and the human imagination. Earth is home to some truly extreme environments that can teach us a great deal about the potential for life beyond our planet. Take, for instance, the hot springs of Yellowstone National Park. These boiling pools teem with extremophiles, organisms that thrive in conditions we once thought inhospitable. The heat and acidity found here mimic conditions on other celestial bodies, such as the hot subsurface of Jupiter's moon Europa. Studying these organisms gives us a clue that life may flourish in similar extreme conditions elsewhere in the universe. Another fascinating example is the deep-sea hydrothermal vents, located along mid-ocean ridges. Here, water spews out from beneath the Earth's crust, heated by volcanic activity. Surprisingly, these vents foster entire ecosystems dependent on chemosynthesis rather than sunlight. The striking biodiversity, including tube worms and giant clams, suggests that life can exist in total darkness, driven by chemical reactions. This opens our minds to the possibility of life in other dark, nutrient-rich environments, like the ocean floors of distant planets. The polar regions of our planet also offer incredible lessons in resilience. In Antarctica, some microorganisms can survive extreme cold and ultraviolet radiation levels. These tiny life forms enter a dormant state, withstanding temperatures far below freezing for extended periods. This endurance fortifies the notion that life could potentially adapt to extreme cold, similar to what we may find on moons like Titan, Saturn's largest moon, where conditions are frigid and hostile. Finally, the Atacama Desert in Chile stands out as one of the driest places on Earth. Here, life perseveres in arid conditions, relying on occasional rain and moisture. Microbial life has been discovered deep in the salt flats, showcasing adaptations to extreme drought. This raises intriguing questions about how life could survive on planets or moons with limited water sources, emphasizing our need to explore and understand these harsh environments both on Earth and beyond. Each of these extreme habitats serves as a window into the resilient nature of life, reminding us that the universe may be more populated with unique life forms than we can imagine. Water plays an undeniably crucial role in the search for extraterrestrial life, primarily because it is a solvent that supports a wide range of chemical reactions essential for life as we know it. This remarkable liquid is the basis for biological processes here on Earth. Life relies on water's unique properties, like its ability to dissolve nutrients and facilitate metabolic processes. As a result, When scientists look for extraterrestrial life, the presence of water becomes a vital indicator or even a prerequisite. In our solar system, bodies such as Mars, Europa, and Enceladus have shown evidence of water, either in liquid form or as ice. On Mars, for instance, researchers have found signs of past water flow and even saltwater brines that may still exist beneath its surface. Europa, one of Jupiter's moons, is fascinating due to its subsurface ocean, hidden beneath a thick, icy crust. The potential for hydrothermal vents on the ocean floor could create the perfect conditions for life to thrive, much like those found in Earth's deep-sea ecosystems. Furthermore, scientists speculate that water does not have to exist solely as a liquid for life to survive. Instead, the presence of water in any form, be it ice or vapor, can provide the necessary ingredients for life to originate or persist in some capacity. This fluid versatility broadens the scope of where we might find life beyond Earth. For instance, researchers are examining transient water vapor in the atmospheres of distant exoplanets, trying to detect the conditions necessary to support life. Ultimately, the quest for extraterrestrial life hinges significantly on the search for water. By focusing on locations where water is present or once existed, we open up incredible possibilities for discovery. The presence of water not only increases the chance of finding life, but also reminds us of the universal conditions that may foster life throughout the cosmos, inviting us to ponder the age-old question of whether we are alone in the universe. Gravitational waves are ripples in the fabric of space-time, caused by some of the most violent and energetic processes in the universe. Imagine dropping a pebble into a still pond. The waves that emanate from the spot where the pebble landed spread outwards. Similarly, when massive objects like black holes or neutron stars collide or accelerate, they create disturbances that travel across space-time, reaching us as gravitational waves. The detection of these waves is a monumental achievement in physics and cosmology. In September of 2015, scientists at the LIGO Observatory recorded the first direct observation of gravitational waves from the merger of two black holes. This groundbreaking event marked a new era in astronomy. For centuries, our exploration of the universe was limited to observing light, whether visible, ultraviolet, or X-ray. Gravitational waves opened a new window, allowing us to perceive cosmic events that were previously undetectable. The implications of this discovery are profound. It not only confirms a major prediction of Albert Einstein's theory of general relativity, but also enhances our understanding of cosmic phenomena. By studying gravitational waves, we can gain insights into the nature of black holes, neutron stars, and even the moments following the Big Bang. Each detection serves as a unique fingerprint, revealing the dynamics of the universe and the processes involved in its evolution. Moreover, the field of gravitational wave astronomy is rapidly growing. As more observatories come online around the world, we expect to uncover countless events and phenomena. This could reshape our understanding of the universe's history and its most elusive elements. In a sense, we are just beginning to listen to the symphony of the cosmos, with gravitational waves serving as a new language for understanding the mysteries of our universe. Gamma-ray bursts are among the most energetic and enigmatic events in the universe, challenging our understanding of cosmic phenomena in profound ways. These bursts, which release more energy in a few seconds than the sun will emit over its entire lifetime, originate from distant galaxies and can outshine entire star systems when they occur. The immense power and brightness of these bursts force scientists to reconsider the mechanics of energy production in the universe and the processes that lead to such extreme outcomes. One of the primary challenges posed by gamma-ray bursts lies in their unpredictability and the emotional roller coaster they create for astronomers. For years, these bursts were detected without any clear understanding of their sources. Some were associated with the collapse of massive stars in supernova explosions, while others seemed linked to the merging of neutron stars. This variety of origins suggests that there may be different mechanisms at play, each producing these staggering bursts of energy in unique ways. Finding the connections between these scenarios continues to puzzle researchers. Moreover, the observation of gamma-ray bursts has opened new doors to understanding the evolution of the universe. They serve as cosmic beacons, illuminating the scales of distances and the ages of the stars and galaxies that host them. Investigating these bursts provides insights into the conditions present in the early universe, shedding light on star formation during that era. With every discovery, we learn more about the life cycles of stars and the dynamic processes that govern cosmic evolution. As researchers continue to study gamma-ray bursts, we find ourselves constantly redefining our knowledge of extreme cosmic events. Each new observation not only enriches our understanding of these extraordinary phenomena, but also invites deeper questions about the nature of the universe. It is a reminder that the cosmos, while vast and complex, still holds many secrets waiting to be uncovered, challenging us to look deeper into the fabric of existence. Pulsars are fascinating celestial objects that serve as highly accurate cosmic clocks. They are rapidly rotating neutron stars, remnants of supernova explosions that emit beams of radiation from their magnetic poles. As these stars spin, the beams sweep across space, and if one of those beams happens to intersect with Earth, we detect a pulse of radiation. This pulsing effect allows astronomers to study the stars in an entirely new way, and their regularity has made them crucial for understanding both stellar evolution and the extreme environments of the universe. The importance of pulsars stretches beyond their captivating flickering. They offer insights into the fundamental laws of physics, especially in terms of gravitational theory. For instance, observing the timing of pulsar signals enables scientists to detect gravitational waves, ripples in spacetime caused by massive events, such as merging black holes. By analyzing the variations in the pulse timing, researchers can even map out the gravitational landscape around these catastrophic events, enhancing our understanding of how massive objects interact in the cosmos. Additionally, pulsars are invaluable for studying the structure and content of our galaxy. By tracking the positions and movements of these stars, astronomers can glean information about the distribution of dark matter and the gravitational influences at work within the Milky Way. This knowledge contributes to the broader understanding of galaxy formation and dynamics, revealing how galaxies evolve over time and how they are shaped by both visible and invisible influences. Moreover, pulsars are being considered for potential applications in navigation beyond Earth. Their predictable signals could be used as a cosmic GPS system for deep space exploration. As we venture further into the universe, pulsars could guide spacecraft and help us navigate through the vastness of space, harnessing their remarkable properties to unlock even more secrets of the universe. Pulsars are not just intriguing phenomena, they are essential tools for unraveling the mysteries of astrophysics, the structure of our galaxy, and even our future explorations of the cosmos. Quasars are among the most fascinating objects in the universe, acting like cosmic lighthouses that illuminate our understanding of distant galaxies and the early cosmos. They are incredibly bright, powered by supermassive black holes at the centers of galaxies. As material falls into these black holes, it heats up tremendously, emitting intense beams of light across various wavelengths, including radio, optical, and X-rays. This brightness allows them to be seen from billions of light years away, making them some of the most distant objects we can observe. When we look at quasars, we are also peering back in time. Because light takes time to travel across the vastness of space, observing a quasar that is billions of light years distant means we are seeing it as it was billions of years ago. This provides a unique window into the conditions of the universe during its early stages, particularly just a few billion years after the Big Bang. By studying the light from these ancient beacons, astronomers can gather valuable information about the formation and evolution of galaxies, their gas and dust content, and the interplay between black holes and their host galaxies. Moreover, quasars can be used to probe the intergalactic medium. As their light travels through space, it interacts with the gas and dust present between galaxies. This interaction leaves imprints on the light, which astronomers can analyze. By examining these spectral lines in the light from quasars, scientists can learn about the composition and density of the universe's matter at different times, enriching our understanding of cosmic structure and evolution. Quasars are not just distant points of light. They are powerful tools that help us unravel the mysteries of the universe. They bridge vast epochs of time and allow us to explore the fundamental processes that shaped the cosmos. Through these incredible objects, we gain insights into the early universe, pushing the boundaries of our knowledge in ways that few other astronomical phenomena can. Dark energy is one of the most mysterious components of our universe, playing a crucial role in its expansion. Observations from the late 20th century revealed that not only is the universe expanding, but that its expansion is actually accelerating. This discovery changed the entire landscape of cosmology, leading scientists to propose dark energy as the driving force behind this accelerated expansion. Imagine the universe as a balloon being inflated. Initially, as the balloon expands, it may inflate at a steady rate. But now picture a scenario where the air pump is pushing air into the balloon at an increasing rate. The balloon expands faster and faster. Dark energy functions somewhat like this accelerating air pump, filling the cosmos with a force that seems to pull galaxies apart more rapidly over time. The implications of dark energy stretch far and wide for our understanding of the universe. For one, it suggests that the universe will continue to expand indefinitely. The fate of galaxies, stars, and even black holes becomes uncertain, as they may drift beyond our observable horizon. This leads to various theories about the ultimate fate of the universe, including scenarios like the Big Freeze, where galaxies become so distant that they fade from view, leaving behind a cold, dark cosmos. Moreover, dark energy raises profound questions about the fundamental nature of reality. What is this enigmatic force? Does it exist as a cosmological constant, or is there more to it? As scientists delve deeper, dark energy challenges us to rethink aspects of physics itself, prompting discussions about the fabric of space, time, and the forces at play in the universe. The pursuit of understanding dark energy remains one of the most thrilling and challenging endeavors in modern astrophysics. The theory of relativity, developed by Albert Einstein in the early 20th century, revolutionized our understanding of time and space, fundamentally challenging long-held beliefs. Prior to this, scientists viewed space as a vast, unchangeable backdrop in which events unfolded, and time as a steady, unyielding flow that was the same for everyone, everywhere. However, Einstein introduced a new perspective. Time and space are intertwined and can change depending on the observer's motion and gravitational influence. One of the central ideas of relativity is that time is not an absolute constant. Instead, it can stretch and compress. For example, if you were to travel at speeds close to that of light, you would experience time at a slower rate than someone remaining on Earth. This phenomenon is known as time dilation. In practical terms, astronauts on a high-speed journey through space would age slightly less than their relatives back on Earth, a concept that sounds like science fiction but has been confirmed through experiments using precise atomic clocks. Space is also affected by motion and gravity in ways that defy ordinary logic. According to Einstein's general theory of relativity, massive objects like planets and stars warp the fabric of space-time around them. This means that the presence of a large mass can bend the path of light and alter the passage of time. Thus, the very structure of the universe is not flat and static but dynamic and affected by energy and mass. The implications of these ideas are vast and profound. They challenge our intuitive notions of existence, suggesting that reality is more interconnected and flexible than we might ever have imagined. By reshaping our understanding, the theory of relativity opens the door to exploring the universe in entirely new ways, reminding us just how much there is still to learn about the cosmos and our place within it. Time dilation is a fascinating phenomenon arising from Albert Einstein's theory of relativity. Simply put, it refers to the difference in the passage of time as observed from different reference frames. This occurs in two primary ways, due to relative velocity and the effect of gravity. In both cases, the speed of objects and the strength of gravitational fields lead to remarkable effects on how time flows. One of the most well-known demonstrations of time dilation is the twin paradox. Imagine two twins. One stays on Earth, while the other travels at a significant fraction of the speed of light in a spacecraft. When the traveling twin returns home, they will find that significantly less time has passed for them compared to their twin who remained on Earth. This difference results from the high velocity experienced by the traveling twin, which causes their onboard time to run slower compared to their siblings' clock. Another striking illustration of time dilation can be seen in the context of strong gravitational fields. Clocks located closer to a massive body, like Earth, tick more slowly than clocks further away. This phenomenon has been directly measured using highly accurate atomic clocks, For instance, when placed at different altitudes, clocks at higher elevations, where the gravitational influence is slightly weaker, run faster than those at lower elevations. These observations confirm how gravity affects the flow of time. Time dilation isn't merely a theoretical concept, it has practical implications too. The Global Positioning System, or GPS, relies on precise timing for accurate location data. The satellites in orbit experience both forms of time dilation. Their velocity causes their onboard clocks to tick more slowly, while they also experience less gravitational pull compared to clocks on Earth. Engineers must account for these time differences to provide accurate location data. Thus, what seems like an abstract scientific concept is woven into the fabric of our technological daily lives. Space-time is a fascinating concept that blends the three dimensions of space with the dimension of time into a singular four-dimensional continuum. Imagine, if you will, a fabric that weaves through the fabric of the universe. This metaphorical fabric stretches and bends in response to the presence of mass. It suggests that events happen not just in a place, but also in relation to when they occur, fundamentally altering how we perceive motion and gravity. Gravity, as we know it, is not merely a force pulling objects together. Instead, in the framework of space-time, gravity emerges from the curvature of this four-dimensional fabric. When a massive body, like a planet or a star, occupies a region of space-time, it creates a dent or a warp in that fabric. Other objects nearby, in their attempt to move through space-time, will follow paths deformed by this curvature. This means that what we perceive as the force of gravity is actually the result of how space-time shapes the motion of objects in its vicinity. The relationship between space-time and gravity was famously formalized by Albert Einstein in his general theory of relativity. This theory transformed our understanding of how the universe operates. Rather than thinking of gravity as an invisible force acting at a distance, Einstein proposed that celestial bodies like the Earth orbits the Sun not because they are being pulled by an invisible string, but rather because they are following the curved paths in space-time created by the Sun's mass. The implications of space-time are profound. They help us understand everything from why planets orbit stars to the behavior of light in the presence of gravity. For instance, light itself bends around massive objects, illustrating the interconnectedness of space and time. In this grand tapestry of the cosmos, space-time offers a holistic view of how everything from the tiniest particles to the largest galaxies interact and move through the universe. It reminds us that the cosmos is not just a collection of isolated objects, but a dynamic, interwoven existence where time and space play essential, inseparable roles. Wormholes, often described as tunnels or shortcuts through the fabric of space and time, have sparked the imagination of both scientists and science fiction enthusiasts alike. Imagine a bridge connecting two distant points in the universe, allowing for instant travel between them. In theory, these cosmic shortcuts could bypass the vast expanses of space we currently navigate, offering a way to traverse the universe that defies our traditional understanding of distance and time. The concept of wormholes arises from the theory of general relativity, formulated by Albert Einstein over a century ago. According to this theory, massive objects warp the space around them, creating gravitational effects that can be visualized as curvatures in a fabric. If we take this further, certain solutions to Einstein's equations suggest the existence of these wormholes, which connect two separate areas of space-time. While they remain speculative, the mathematical framework supporting wormholes has encouraged many to explore their potential. The implications for space travel are profound. If wormholes could be stabilized and harnessed, they might enable humanity to reach far-off galaxies within a matter of moments, rather than the millions of years it would take with conventional propulsion methods. Additionally, they raise fascinating possibilities for time travel, allowing one to traverse not just space, but potentially also the temporal dimension, stepping into the past or the future with the right conditions. However, while the theoretical foundation is compelling, creating or finding a traversable wormhole presents monumental challenges. Current scientific understanding suggests that exotic matter, substances that would have negative energy density, would be required to keep a wormhole open and stable. As of now, such materials remain purely hypothetical, and there are many unanswered questions surrounding their existence. Thus, while wormholes capture our imagination and expand our understanding of the universe, They also remind us of the vast mysteries yet to be uncovered in the cosmos. Understanding the curvature of space-time, an idea that originated from Albert Einstein's theory of general relativity, is essential for grasping how mass influences the fabric of the universe. Scientists measure and observe this curvature mainly through two powerful methods: gravitational lensing and the tracking of planetary motion. Gravitational lensing occurs when a massive object, such as a galaxy or cluster of galaxies, lies between us and a more distant source of light, like a quasar. The strong gravitational field of the intervening mass bends the light from this background object. This bending can create multiple images or arcs around the mass, allowing astronomers to observe and measure the degree of curvature in space-time that the mass creates. By analyzing these images, scientists can draw conclusions about the mass distribution and the nature of the dark matter that may be present. Another approach involves observing the motion of planets and other celestial bodies. The way these bodies move can be influenced by the curvature of space-time around more massive objects. For instance, when studying the orbits of planets in our solar system, scientists use precise measurements of distances and velocities to confirm the predictions made by general relativity. They find that the orbits are not perfect ellipses, but exhibit slight variations due to this curvature. This is especially notable in the case of Mercury, whose orbit precesses or shifts over time, a phenomenon that was first observed and explained through the lens of Einstein's theories. Furthermore, the use of gravitational waves has expanded our understanding of space-time curvature significantly. When massive objects like black holes or neutron stars collide, they create ripples in space-time known as gravitational waves. Detectors like LIGO and Virgo have captured these waves, confirming predictions of space-time distortion in extreme conditions. The analysis of these waves allows scientists to glean more information about the mass and energy of their sources, all while deepening our comprehension of space-time itself. The multiverse theory is a fascinating concept that expands the traditional notion of our universe, suggesting the existence of multiple, perhaps infinite universes beyond our own. Different interpretations of this theory propose various ways these parallel universes might arise. One prominent interpretation is the bubble universe concept, which suggests that during cosmic inflation, distinct bubbles can form, each representing a separate universe with its own unique properties. These bubbles drift apart, each evolving according to different physical laws, creating a vast multiverse landscape. Another interpretation is the many worlds hypothesis, which stems from quantum mechanics. In this view, every time a quantum event has multiple possible outcomes, all possibilities actually occur, but in separate, branching universes. This means that for every decision you make, countless versions of yourself exist in universes where you chose differently. This interpretation radically reshapes our understanding of reality, suggesting that every action and its consequences unfold in their own distinct universe. Cosmic string theory also contributes to the multiverse concept. In this scenario, the universe behaves like a vast quilt, with cosmic strings acting as the threads that separate various patches of reality. Each patch could possess different fundamental properties, leading to potentially habitable or completely uninhabitable environments. These strings could provide the connections and divisions between various universes, highlighting both their individual uniqueness and their interaction with each other. Lastly, there's the theory of brains from string theory, where our universe is just one three-dimensional brain within a higher dimensional space. Other brains could represent different universes, occasionally colliding with ours in events that might have mirrored the Big Bang. The diverse interpretations of the multiverse not only stretch our imaginations about the fabric of reality, but also challenge our understanding of existence itself, igniting debates in scientific, philosophical, and even spiritual realms. Each perspective adds a layer of depth to how we think about parallel universes, making the multiverse a compelling topic in both cosmology and human thought. String theory stands as a bold contender in the landscape of fundamental physics, proposing an intriguing framework that suggests our universe is composed of tiny, vibrating strings rather than the point-like particles of conventional physics. These strings, which can be as small as 10 to the minus 33 centimeters, resonate at different frequencies. Each vibration corresponds to a different particle, which means that the variety of particles and forces we observe could arise from a single fundamental entity. Now, when we venture into the discussion of the multiverse, string theory adds even more layers of complexity. The fabric of string theory allows for the existence of multiple dimensions beyond our familiar 3 of space and 1 of time. In fact, string theory posits up to 11 dimensions. The unique configurations of these additional dimensions could lead to a multitude of distinct universes, each governed by its own physical laws and constants. This concept gives rise to the idea that we might not just reside in a single universe, but rather in a vast tapestry of different realms, collectively known as the multiverse. Moreover, string theory includes the notion of landscape, which refers to a vast array of possible solutions to fundamental equations. Each solution corresponds to a unique universe with its own set of physical laws. This means that there might be universes where gravity is stronger or weaker, or where time behaves differently than what we experience. Such a multitude of universes could help explain why our own universe appears so finely tuned for the emergence of life. In sum, string theory not only offers a potential framework for understanding the fundamental nature of particles and forces, but also opens the door to contemplating the existence of a multiverse. This interplay between the intricate vibrational patterns of strings and the myriad possibilities of different universes captivates the imagination and hints at a far more complex reality than we once dared to consider. The journey into the unknown through string theory and the multiverse serves as a reminder of the profound mysteries that still lie ahead in our quest for understanding the cosmos. The multiverse theory, a fascinating concept suggesting that our universe is just one of countless others, presents a series of formidable challenges for scientists. One of the primary obstacles is that the other universes, or multiverses, may be fundamentally different from our own, making them incredibly difficult, if not impossible, to observe directly. This lack of observational evidence is a major hurdle, as science heavily relies on tangible data to support or refute theories. Unlike planets or stars that we can study with telescopes, these alternate realms might exist in dimensions or forms that are completely inaccessible to our current technology. Another challenge lies in the sheer number of potential universes posited by multiverse theories. Each universe could have its own physical laws and constants, leading to nearly infinite variations. This immense diversity complicates the development of testable predictions. Scientists thrive on formulating hypotheses that can be tested with experiments or observations. Without specific predictions that could be verified or falsified, the multiverse concept risks becoming more philosophical than scientific, as it raises existential questions about reality itself, rather than presenting concrete avenues for investigation. Then, there is the question of internal consistency within the existing framework of physics. The multiverse theory often emerges from interpretations of quantum mechanics and cosmology, which have their own complexities. Researchers must ensure that any attempt to incorporate the multiverse into established scientific paradigms doesn't contradict well-tested principles. Connecting new ideas to existing theories in a way that feels coherent and valid demands creativity as well as rigorous analytical thinking. Finally, the wider acceptance of the multiverse theory faces philosophical implications. Traditional views of scientific inquiry emphasize observable and repeatable phenomena. Some argue that if other universes exist beyond our observable realm, they fall outside the boundaries of empirical investigation. This raises the question, can ideas that cannot be tested truly be considered science? These challenges collectively shape the discourse around the multiverse, highlighting the interplay between theoretical exploration and empirical validation in our quest to understand the cosmos. The anthropic principle offers a fascinating lens through which we can consider our existence in the universe. It suggests that the universe must have the properties that allow life to develop, because we, as conscious beings, are here to observe it. This principle comes into sharper focus when we explore the concept of the multiverse, which posits that our universe is just one of potentially countless others, each with different physical laws and constants. If the multiverse theory holds true, then the implications of the anthropic principle become even more profound. In a vast collection of universes, each one could take on a different configuration. Some may be structured in a way that life could never emerge, while others might foster conditions ripe for existence. Our universe, with its finely tuned constants like the strength of gravity or the nature of electromagnetic forces, could be one of many that happen to allow for life. In this context, we exist not because this universe was necessarily unique, but because it is one of the few where life can emerge and evolve. This understanding leads to intriguing questions about the nature of our reality. Are the laws of physics in our universe coincidental, or do they arise from a larger framework made possible by the multiverse? Life, as we know it, might be an inevitable product of a universe that supports it, but through the anthropic lens, we also recognize that our particular circumstances may be incredibly rare. It invites a sense of humility and wonder as we contemplate the staggering diversity that could exist beyond our realm. In this exploration of the anthropic principle and the multiverse, we are left with more than just scientific insights. We are prompted to ponder our place in the cosmos and the myriad possibilities of existence. This intriguing dialogue between the laws that govern our universe and the question of why we are here deepens our fascination with both science and philosophy, ultimately enriching our understanding of the universe and our role within it. Quantum mechanics, often described as the science of the very small, presents a fascinating framework for understanding our universe, and intriguingly, it lends itself to the multiverse concept. At its core, quantum mechanics deals with the behavior of particles at the atomic and subatomic levels, where outcomes can seem probabilistic rather than deterministic. This inherent uncertainty is pivotal to our understanding of parallel realities. One of the key ideas from quantum mechanics involves superposition. In simple terms, this means that particles can exist in multiple states at once until they are observed or measured. This principle has led to suggestions that every possible outcome of a quantum event actually occurs, but in separate branching realities. Imagine flipping a coin. While it lands in one state in our reality, quantum mechanics proposes that in another reality, it may have landed as heads. Another fascinating aspect is the many worlds interpretation, which posits that all possible histories and futures are real and occur in a vast number of universes. According to this interpretation, every time a quantum event happens, our universe splits into different branches, each representing a different outcome. This means that there might exist countless versions of us in universes where different choices were made or different events transpired. Thus, quantum mechanics not only challenges our traditional notions of reality, but also supports the idea that our universe might be just one of countless others. This enticing connection encourages us to rethink everything we know about existence, illustrating the remarkable ways in which the smallest particles in the universe could imply the vastness of the multiverse itself. It is a profound reminder of how interconnected and complex the cosmos truly is. The existence of dark matter is supported by a variety of astronomical observations that reveal its profound influence on the universe. One of the most compelling pieces of evidence comes from the motion of galaxies within galaxy clusters. When scientists measure the speed at which these galaxies orbit around their center, they find that the visible matter, like stars and gas, does not account for the gravitational forces needed to hold them together. The velocities suggest there is far more mass present than what we can observe, indicative of a hidden mass, now referred to as dark matter. Another critical piece of evidence lies in the structure of the universe on a cosmic scale. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, show tiny fluctuations in temperature that correspond to the density of matter in the early universe. The pattern of these fluctuations matches predictions that require a significant amount of dark matter to explain how structures like galaxies formed and clustered over billions of years. Without dark matter, our current model of cosmic evolution would simply not hold. In addition to these observations, gravitational lensing provides further support for dark matter's existence. This phenomenon occurs when massive objects, like clusters of galaxies, bend the light from objects behind them. The amount of bending indicates mass, and again, there's evidence of mass that cannot be linked to the visible matter around us. This unseen mass reveals itself in the way it alters the paths of light, leading us to conclude that dark matter must make up a substantial portion of the universe. In contrast to conventional matter, which includes everything we can see and detect from stars to planets, dark matter does not emit, absorb, or reflect light, making it completely invisible to our current instruments. While conventional matter interacts through the fundamental forces of gravity, electromagnetism, and the strong and weak nuclear forces, dark matter only seems to interact gravitationally. This chasm between the two types of matter fundamentally shapes how scientists study and understand the universe, leaving an intriguing mystery for researchers to uncover as they delve deeper into the cosmos. Gravitational lensing is a fascinating phenomenon that occurs when massive objects, like galaxies or clusters of galaxies, bend the light from distant objects behind them. This effect is a consequence of Einstein's theory of general relativity, which tells us that mass curves the fabric of space and time. When astronomers observe this bending of light, they can infer the presence and distribution of invisible dark matter, which significantly influences the gravitational pull of these massive objects. To map the distribution of dark matter, scientists first identify the bright background galaxies whose light is being distorted by a foreground galaxy or cluster. By analyzing the shapes and orientations of these background galaxies, they can recognize patterns of distortion that indicate how much mass is present in the foreground object. The more light is bent, the more mass there is. This allows researchers to create a map that reveals the concentration of dark matter, even though it cannot be seen directly. Using advanced telescopes and specialized algorithms, scientists track thousands of background galaxies, compiling extensive data on how their images are warped. This process is akin to piecing together a cosmic puzzle. The resulting maps not only unveil areas with large masses of dark matter, but also help in understanding its role in the formation and evolution of galaxies over billions of years. This innovative technique has revolutionized our understanding of the universe. It has provided compelling evidence that dark matter exists, making up about 25% of the universe's total mass and energy. As researchers delve deeper, they continue to refine their methods, shining light on the elusive nature of dark matter and its critical role in the structure of the cosmos. In the vast expanse of the universe, our understanding has unraveled some astonishing mysteries, chief among them being the concept of dark energy. This enigmatic force, which makes up about 70% of the total energy content in the universe, plays a crucial role in its accelerated expansion. To put it simply, while gravity pulls matter together, dark energy seems to push the universe apart. The discovery of dark energy dates back to the late 20th century, when astronomers observed that distant galaxies were moving away from us faster than expected. This observation was unexpected and led scientists to reconsider their understanding of cosmic forces. They proposed that dark energy acts as a sort of anti-gravity, exerting a repulsive force that overcomes the attractive pull of gravity on cosmic scales. It is this repulsive force that drives the acceleration of the universe's expansion. One of the most intriguing aspects of dark energy is its uniformity. Unlike ordinary matter and energy, which clump together due to gravitational attraction, dark energy appears to be evenly distributed throughout space. This means that no matter where you look in the universe, the influence of dark energy remains constant. As the universe evolves, even as galaxies and structures come together under gravity, dark energy's consistent push is what keeps everything expanding. Scientists are still unraveling the full story of dark energy. Some theories suggest it might stem from a property of space itself, while others hint at new physics that we have yet to discover. Regardless of its origin, dark energy remains central to our understanding of the universe's fate, leading many to wonder what the ultimate state of our cosmos will be as it continues to expand into the unknown. The discovery of dark energy has fundamentally reshaped our understanding of the cosmos. Prior to this revelation, scientists believed that the universe was gradually slowing down its expansion due to the gravitational pull of matter. This view was largely based on the observable evidence of celestial bodies behaving as if they were bound by gravity, suggesting a universe that would eventually collapse or stabilize. However, the identification of dark energy has introduced a compelling twist to this narrative. Dark energy is a mysterious force driving the accelerated expansion of the universe, contradicting the earlier assumption that gravity would dominate over vast distances. This phenomenon was first suggested in the late 90s, when astronomers observed distant supernovae that were fainter than expected. Rather than moving away from us at a steady pace, these supernovae revealed that the expansion of the universe is not only continuing but speeding up. This insight has prompted scientists to revisit centuries of cosmic science, and consider a universe that is ultimately destined for a much different fate than previously thought. Now, rather than a cosmos that might contract back on itself, the predominant thought is that the universe will continue to stretch out indefinitely. This has profound implications for everything from the fate of galaxies to the very structure of the universe. As dark energy composes roughly 70% of the total energy content of the universe, understanding its nature and behavior is crucial. It suggests that even the fabric of space-time itself is subject to forces that challenge our classic notions of gravity and cosmic equilibrium. The mystery of dark energy compels us to explore deeper questions about the universe's origin and destiny. As scientists investigate the properties and possible origins of this enigmatic energy, we find ourselves pushed towards new frontiers in physics. The study of dark energy offers not just answers about how our universe behaves today, but it nudges us into pondering what lies ahead in the cosmic journey. The quest for knowledge continues, fueled by curiosity and the desire to comprehend our ever-expanding universe. Dark matter and dark energy are two of the universe's most elusive mysteries. Together, they comprise about 95% of the cosmos, yet they remain largely undetectable. Scientists are fervently conducting a variety of experiments and observational studies to unravel their secrets, and the excitement in the scientific community is palpable. One significant effort comes from large-scale observatories like the Vera C. Rubin Observatory in Chile. This facility aims to map the Milky Way and beyond using a technique called gravitational lensing. When light from distant galaxies passes near massive objects like clusters of dark matter, it bends. By measuring this distortion, researchers hope to locate and understand the distribution of dark matter in the universe, helping to uncover its properties. In the realm of particle physics, experiments such as those occurring at the Large Hadron Collider in Switzerland seek to detect potential dark matter particles. Through high-energy collisions, scientists examine what emerges from those interactions, looking for signs of exotic particles that might hint at the makeup of dark matter. Additionally, underground laboratories across the world, like the Large Underground Xenon or Lux Zeppelin projects, are attempting to capture dark matter particles through sensitive detectors shielded from cosmic rays. Meanwhile, dark energy, thought to drive the universe's accelerating expansion, is being studied through projects like the Dark Energy Survey, which maps hundreds of millions of galaxies. By analyzing their distribution and movement, cosmologists aim to understand the role of dark energy in shaping the universe's fate. Each study, each observation, brings us closer to a clearer picture of these enigmatic components, ensuring that the quest for knowledge continues to ignite curiosity among both scientists and enthusiasts alike. Extremophiles are remarkable organisms that thrive in conditions once thought to be uninhabitable. They can survive in environments with extreme temperatures, acidity, salinity, or pressure. By studying these resilient life forms, scientists have begun to challenge and expand our understanding of what defines life itself. These organisms inspire us to rethink the boundaries of life, especially in relation to environments beyond our own planet. One significant insight from extremophiles is that life can exist in forms previously considered impossible. For instance, certain bacteria can flourish in boiling hot springs or in the frigid depths of the ocean. They can withstand radiation levels that would be lethal to humans. This suggests that life could potentially exist in similar extreme conditions on other celestial bodies, such as the icy moons of Jupiter and Saturn, or even on distant exoplanets. As a result, extremophiles shape the criteria we use to search for life beyond Earth, emphasizing that our expectations of habitability need to be broad and inclusive. Moreover, extremophiles also offer insights into the biochemical pathways that sustain life. Many of these organisms utilize unique metabolic processes that allow them to extract energy from their harsh environments. For instance, some can convert sulfur or methane into energy, expanding the knowledge of chemical processes that support life. This understanding is critical when considering the possibility of extraterrestrial life, as it opens up new avenues for exploration in environments previously deemed hostile. Finally, the study of extremophiles has practical implications on Earth as well. Their unique adaptations are being harnessed for biotechnology, such as developing new enzymes for industrial processes or creating more resilient crops. Extremophiles not only redefine our search for life beyond Earth, but also enrich our understanding of life's incredible diversity and resilience right here in our own biosphere. Through them, we learn that life's tenacity is far more extensive than we ever imagined, expanding our definitions and preconceived notions about the existence of life in the universe. In the quest to uncover extraterrestrial life on Mars, scientists and engineers design instruments that can operate at various voltages, typically ranging from 5 to 24 volts. These voltages are essential for powering the intricate machinery used in missions, such as rovers and landers, which analyze soil and atmospheric samples. This range of voltage is particularly important because it balances the need for efficient energy consumption with the capacity to deliver enough power for the instruments to function effectively. For instance, the Mars rovers, like Curiosity and Perseverance, utilize sophisticated tools like lasers and spectrometers that require specific voltages to operate. These instruments are capable of performing complex analyses, such as determining the chemical composition of Martian rocks and soil, which could hint at past microbial life. Their onboard systems are designed to maximize the efficiency of the available energy generated, often by solar panels, ensuring they can continue to gather data even in the harsh environment of Mars. Moreover, various temperature extremes on Mars necessitate robust engineering to maintain optimal operating conditions for these instruments. With temperatures that can drop significantly at night, energy management becomes crucial. The voltage systems are not only designed for function but also for resilience, ensuring that these missions can survive the Martian winters while continuing their life-detecting endeavors. Ultimately, while the exact voltage levels can vary depending on the specific mission and its objectives, the quest for life on Mars hinges significantly on the power these instruments utilize. With every volt, scientists edge closer to answering one of humanity's most profound questions: are we alone in the universe? The icy moons of our solar system, particularly Europa and Enceladus, are intriguing destinations in the quest to understand potential life beyond Earth. These moons orbit giant planets and are thought to harbor vast oceans beneath their thick icy crusts. The discovery of these subsurface oceans raises exciting possibilities. If there is liquid water trapped beneath the surface, could it support life? Europa, one of Jupiter's moons, is covered in a layer of ice, but scientific evidence suggests that beneath this ice lies a salty ocean in contact with a rocky seafloor. This interaction between water and rock can create a rich chemical environment, potentially underpinned by geothermal energy, much like hydrothermal vents we find in Earth's deep oceans. These conditions could mimic those where life thrives on our own planet, igniting the hope that similar environments might exist elsewhere in the universe. Enceladus, a moon of Saturn, further fuels this optimism. In 2005, scientists discovered geysers erupting from its surface, releasing plumes of water vapor and ice particles into space. Analyzing these plumes revealed not only water but also organic molecules, along with salts and other chemicals linked to potential habitability. This finding supports the concept that Enceladus's subsurface ocean might be suitable for life, indicating that the ingredients for life, including water and organic compounds, are present. The study of these icy moons does more than just hint at life. It expands our understanding of where life could exist. Earth-based life has shown remarkable adaptability, suggesting that life, if it exists elsewhere, could be very different from what we know. As we continue to explore these alien worlds, we learn more about the diverse environments that might sustain life, making the icy moons not just distant, chilly bodies, but also promising frontiers in our quest for the cosmic neighbors we have yet to discover. Sending missions to distant planets in our solar system comes with a myriad of challenges that can be both complex and fascinating. One of the primary hurdles is the sheer distance itself. For instance, a journey to Mars, which is relatively close to Earth, can take around 6 to 8 months. When we consider the outer planets like Jupiter or Saturn, the travel time extends significantly, causing planners to think not only about propulsion techniques, but also the sustainability of missions that could last many years or even decades. Communication presents another major challenge. The vast distances involved mean that signals take considerable time to travel between Earth and the spacecraft. For example, transmissions to Mars can take about 13 minutes one way, while signals to Neptune can take over 4 hours. This delay complicates mission control as there is a lack of real-time communication. Engineers must ensure that spacecraft can perform autonomously, making critical decisions without immediate guidance from Earth. Additionally, the harsh environments of distant planets pose significant obstacles. For example, the extreme cold of ice giants like Uranus and the intense radiation near Jupiter require specially designed equipment and materials. Instruments must be robust enough to withstand everything from extreme temperatures to corrosive atmospheres. This necessitates extensive testing and often leads to increased costs and longer development times for the missions. Finally, the unpredictability of space itself adds an element of uncertainty. Asteroids, solar flares, and unexpected technical malfunctions can jeopardize mission objectives. Consequently, mission planners must prepare for various contingencies, ensuring crews and instruments can adapt to rapidly changing conditions. Even with these challenges, the quest to explore distant planets remains one of humanity's most exciting frontiers, promising insights into the mysteries of our solar system. Astrobiologists use a combination of astronomical observations, chemical analysis, and theoretical models to predict the potential for life on exoplanets located in distant star systems. The search for life revolves around a few key criteria, the most important of which is the planet's location within what's known as the habitable zone. This is the region around a star where conditions might be just right for liquid water to exist, which is considered essential for life as we know it. Once a candidate planet is identified, scientists look at its atmosphere. They analyze how starlight interacts with the planet's atmosphere using advanced instruments on telescopes. These observations help scientists identify specific gases that may indicate biological processes. For example, the presence of gases like oxygen or methane in significant quantities can suggest that life might be active on that planet, as we observe similar phenomena here on Earth. Additionally, astrobiologists also consider the planet's temperature, surface conditions, and geological activity. These factors can influence the availability of water and essential elements that life needs to thrive. For instance, a rocky planet similar to Earth that orbits within the habitable zone of a stable star is more likely to support life. The age and type of star are also critical. Stars that are too bright or too variable may not offer the right conditions. Finally, the study of extreme environments on our own planet provides invaluable insight. By examining life forms that survive in harsh conditions, such as deep-sea hydrothermal vents or Arctic ice, scientists can expand their understanding of where life could potentially exist beyond Earth. This ongoing exploration fuels our understanding and ignites our imagination about the potential for life elsewhere in the universe. Cosmic rays are high-energy particles that travel through space and occasionally collide with Earth's atmosphere. When these particles enter our atmosphere, they can create a cascade of secondary particles, which can have various effects. For instance, they can lead to the production of clouds in the atmosphere, influencing weather and climate patterns in subtle ways. Additionally, cosmic rays can affect electronic systems and satellites, leading to data disturbances or malfunctions. The origins of cosmic rays are fascinating, as they come from a broad array of sources. Some are generated from our own sun, especially during solar flares and coronal mass ejections, which can send streams of charged particles hurtling through space. However, the most energetic cosmic rays are believed to originate from outside our solar system, possibly from supernova explosions, neutron stars, or black holes in distant galaxies. These events can produce particles with energies millions of times greater than those we can achieve with our most powerful particle accelerators. Interestingly, about 1 in every 5 cosmic rays that hit the Earth's surface is made up of protons. The rest include a variety of heavier elements, like helium nuclei, and even heavier atomic nuclei, which are sometimes referred to as heavy cosmic rays. Earth's magnetic field and atmosphere serve as a shield, absorbing many of these rays, but a small fraction reaches the surface, where they can lead to interesting scientific phenomena. Researchers continue to study cosmic rays to better understand their behavior and origins. They play a critical role in astrophysics and have implications for our understanding of the universe. As we learn more about these mysterious particles, we can better grasp both their impact on our planet and their journey through the cosmos. The Fermi paradox arises from a simple yet profound observation. Given the vast size of the universe and the enormous number of stars similar to our Sun, we might expect to see abundant evidence of extraterrestrial civilizations. Yet, despite decades of searching and billions of potentially habitable planets, we have not found any conclusive signs of intelligent life beyond Earth. The name comes from the renowned physicist Enrico Fermi, who famously asked, "Where is everybody?" during a conversation about the possibility of alien life. This paradox poses a couple of intriguing implications about extraterrestrial civilizations. One suggestion is that intelligent life may be exceedingly rare. The unique conditions that allowed life to thrive on Earth might not be replicated elsewhere in the universe. Factors like the right distance from a star, suitable atmospheric conditions, and the planet's geological stability could be a rare combination. If life is uncommon, the silence of the cosmos becomes understandable. Another possibility is that intelligent civilizations are common, but they tend to self-destruct before they can explore or communicate with the galaxy. This theory suggests that the technological advancements that could lead civilizations to space exploration might also lead to their downfall, be it through nuclear warfare, climate change, or other self-inflicted crises. In this view, the absence of contact could be seen as a warning, a reminder of the dangers that accompany progress. Finally, there's the more enigmatic suggestion that we simply do not recognize the signs of life when we encounter them. Extraterrestrial civilizations may communicate in ways we can't perceive, or may choose not to interact with us for reasons we cannot comprehend. This leads to the possibility that the universe is teeming with life, yet it remains hidden in plain sight, encouraging us to reconsider our parameters for intelligence and communication. The Fermi paradox challenges us to ponder not just the existence of life beyond our planet, but also the very nature of existence itself. Fast radio bursts, or FRBs, are one of the most fascinating phenomena in the universe. Discovered just over a decade ago, these brief but intense bursts of radio waves last only milliseconds, but can emit as much energy as the sun does in an entire day. Their origins are still largely unknown, which makes them a tantalizing subject of research in astrophysics. Each new FRB offers unique insights into cosmic events, challenging our understanding of the universe. One of the key lessons from studying FRBs is their ability to probe the interstellar medium. The variations in their signals as they travel through space provide valuable information about the density and composition of matter in the universe. By analyzing how the bursts are dispersed and delayed as they reach Earth, scientists can infer details about the regions of space they have traveled through, revealing much about the invisible matter that fills the cosmos. This information can help refine our models of the universe's structure and evolution. Despite the progress made in understanding FRBs, they still present several mysteries. For instance, the exact mechanisms that create these bursts remain uncertain. While some hypotheses suggest they could come from magnetars, hypermagnetic neutron stars, others consider exotic scenarios, such as interactions with dark matter. Each potential explanation opens up a myriad of questions, prompting researchers to explore deeper into both the physical processes that lead to FRBs and the nature of the cosmos itself. The elusive nature of FRBs keeps scientists on their toes. As we develop more sophisticated tools and observatories, we hope to unravel the secrets these bursts hold. Each discovery not only enhances our knowledge of extreme astrophysical events, but also encourages a deeper inquiry into the fundamental principles of our universe. With every burst that we detect, new chapters in the cosmic story are written, sparking our imagination and curiosity about what lies beyond our observable horizon. The cosmic web is a fascinating network that shapes the distribution of galaxies and matter throughout the universe. This web consists of vast, intricate filaments made up of dark matter and gas, creating a framework that connects galaxies across immense distances. Imagine it as a spider's web, with the strands representing these filaments and the intersections serving as the locations for galaxy clusters and superclusters. At the heart of this cosmic web, we find areas of high density known as nodes, where galaxies congregate in large clusters. These clusters are not randomly distributed. They are strategically positioned along the filaments of dark matter, which acts like a scaffolding for the universe. The filamentary structure guides the movement of galaxies, influencing their formation and growth over billions of years. As galaxies traverse these filaments, they interact with one another, exchanging gas and feeding into the process of star formation. In addition to shaping the locations of galaxies, The cosmic web also affects the way matter is distributed in the universe. The large-scale structure of the web has significant implications for understanding the evolution of the cosmos. For example, regions that are more densely packed with dark matter lead to more vigorous gravitational interactions, which can trigger the formation of new galaxies or lead to mergers between existing ones. Ultimately, the cosmic web represents the largest-scale organization of matter in the universe, providing a framework that governs galactic evolution and distribution. As astronomers continue to study this complex structure, they gain insights into the underlying physics of the universe, enhancing our understanding of how galaxies and matter have evolved from the Big Bang to the cosmos we see today. Dark flow is a fascinating phenomenon observed in the universe that suggests vast structures are influencing the movement of galaxy clusters. Essentially, while galaxies typically move in a way that is consistent with the overall expansion of the universe, dark flow hints at an overarching influence that is drawing some clusters toward a particular region in space. This movement appears to be radially directed toward a specific area beyond our observable cosmos, which has sparked significant interest among astronomers and cosmologists. The implications of discovering dark flow are profound. If certain galaxy clusters are moving in this unique trajectory, it suggests that there are large and unseen structures, perhaps even superclusters of galaxies or cosmic filaments, influencing the dynamics of these clusters. This goes against the prevailing idea that the universe is largely isotropic or uniform in all directions. Rather, dark flow could indicate that the large-scale structure of the universe is more complex and interconnected than we previously understood. Moreover, dark flow raises questions about the boundaries of our observable universe. If these structures exist beyond what we can currently see, it challenges the limits of human observation in cosmology. It nudges us to rethink our understanding of cosmic inflation and the distribution of matter and energy in the universe. This discovery encourages scientists to explore the universe beyond the visible horizon, expanding our quest to understand both what exists and how it acts. In sum, dark flow serves as a reminder of the mysteries that still surround our universe, acting as a gateway to potential new discoveries. As researchers delve deeper into this intriguing phenomenon, it may provide critical insights into the formation and evolution of cosmic structures, ultimately enriching our grasp of how the universe operates on a grand scale. Each piece of the cosmic puzzle, including dark flow, adds to our narrative of the universe and propels our curiosity into the infinite reaches of space. The ultimate fate of the universe is a question that has captivated scientists and philosophers alike for generations. Several theories have emerged, shaped by our understanding of cosmic expansion, the nature of dark energy, and the forces governing the universe. One of the prominent ideas is known as the Big Freeze, or heat death. This theory suggests that as the universe continues to expand, it will ultimately grow increasingly cold and dark. Stars will burn out, galaxies will drift apart, and the universe will approach a state of maximum entropy, where no energy gradients exist to sustain physical processes, leading to a cold, lifeless expanse. Another intriguing scenario is the Big Crunch. This concept posits that if the density of matter in the universe is high enough, gravitational forces might eventually halt the expansion and cause the universe to collapse in on itself. This would result in a dramatic reversal where galaxies, stars, and planets all coalesce, spiraling back towards a singular point. In this cycle, matter may again be compressed to extremely high densities, potentially leading into another Big Bang. It's a striking vision of cosmic life cycles, suggesting that the universe might not just end, but could enter a new birth phase. Complementing these ideas is the theory of the Big Rip. This hypothesis stems from the role of dark energy, a mysterious force that appears to be driving the accelerated expansion of the universe. If dark energy continues to increase in strength, it could eventually tear apart galaxies, stars, and even atomic structures, leading to a catastrophic end where everything is ripped apart at the fabric of space and time. Finally, there's the concept of a cyclic universe, which argues that rather than having a single beginning and end, the universe undergoes endless cycles of expansion and contraction. Each cycle may begin with a Big Bang and end with a Big Crunch, only to start the process anew. This notion challenges our conventional understanding of linear time, suggesting a universe in perpetual motion, continuously evolving in phases. Each theory offers a unique glimpse into the potential destinies awaiting our universe, continuing to invite exploration, inquiry, and awe from all who ponder the cosmos. The fate of the universe has fascinated scientists and philosophers alike for centuries, and two prominent scenarios stand at the forefront of these discussions: the Big Crunch and heat death. The Big Crunch envisions a universe that eventually reverses its current expansion. According to this theory, the gravitational attraction of matter would gradually overcome the repulsive force of dark energy, leading to a slowdown in the expansion. Ultimately, galaxies, stars, and all forms of matter could collapse back into a singular point, much like the explosion that created it in the first place. This scenario prompts thoughts of cosmic rebirth, where the universe would reset itself, potentially beginning an entirely new cycle of existence. In contrast, the scenario known as heat death paints a far more subdued conclusion for our universe. It suggests that as the universe continues to expand, stars will exhaust their nuclear fuel, leading to a gradual dimming of the cosmos. Over countless billions of years, galaxies will drift apart, and the temperature of the universe will approach absolute zero. This slow decline into darkness would mean that there are effectively no more stars forming, and the remnants of celestial bodies would slowly fade away into cold, lifeless space. In this scenario, the universe reaches a state of maximum entropy, where all energy is uniformly distributed, making it impossible for any complex processes or structures to emerge. Both scenarios illustrate the dramatic possibilities of cosmic endings, yet they strike very different tones. The Big Crunch is filled with the energy of collapse, as if the universe is drawing itself into a final, intense embrace. In contrast, heat death represents a silence, like an extinguishing of the lights in a vast cosmic theater, echoing the idea that even the grandest entities eventually fade into nothingness. What's particularly captivating is how these models reflect our understanding of fundamental physics and the forces that govern our universe. As we gather more observational data, especially from distant galaxies and cosmic radiation, the debate over which scenario might prevail continues. Perhaps the ultimate fate of the universe will surprise us, revealing even more mysteries about the fabric of existence as we seek to answer the profound question of how it all might end. The concept of a cyclical universe posits that our cosmos undergoes repeating cycles of expansion and contraction, a far cry from the more widely accepted view of a continuous one-time expansion since the Big Bang. Evidence supporting this idea draws from various fields, including observations of cosmic microwave background radiation and the distribution of galaxies in the universe. One pivotal piece of evidence lies in the characteristics of cosmic microwave background radiation, which is a remnant from the early universe. Some scientists propose that the slight irregularities observed in this radiation could indicate a series of universal phases, hinting at rebirths of the universe. Moreover, studies of gravitational waves and dark energy feed into this narrative. These phenomena suggest the universe's behavior may not be as simple as we tend to think, and invite further exploration into possible oscillatory models. The idea of a cyclical universe also relates closely to existing theories of cosmology, particularly those involving string theory and quantum gravity. These theories suggest that the fundamental forces of the universe may allow it to go through continuous cycles. For instance, in some models, the end of one universe could create conditions suitable for the next to emerge, which fits neatly into the cyclic view. While mainstream cosmology primarily supports the singular Big Bang event, these alternative theories are gaining traction. As our observational tools sharpen and our understanding deepens, we may discover more evidence that either reinforces or challenges our current perspectives on the nature of the cosmos. The exploration of a cyclical universe ultimately enriches our quest to understand the enigmatic, ever-unfolding story of existence itself. Understanding stellar evolution has profound implications for predicting the future of galaxies. At the heart of this concept lies the life cycle of stars, which guides the development and composition of galaxies over cosmic time. Stars are born from clouds of gas and dust, live out their lifespans, and ultimately die, scattering elements into space. This cycle of birth, life, and death not only shapes individual stars but also influences the evolutionary trajectory of their host galaxies. As stars evolve, they undergo various processes that affect the chemical makeup of their environments. For instance, when massive stars reach the end of their lives, they explode as supernovae, distributing heavy elements throughout the galaxy. This not only enriches the interstellar medium, the space between stars, with the building blocks for new stars and planets, but also alters the gravitational dynamics and thermal conditions of the galaxy. Consequently, researchers can apply these insights to model how galaxies might change over billions of years. Moreover, the interactions between stars, such as forming binary systems or colliding in clusters, can drastically impact stellar evolution. These interactions can induce phenomena like gamma-ray bursts or the generation of neutron stars or black holes, which provide significant feedback mechanisms that can influence star formation rates. By integrating this knowledge into simulations, scientists can better predict when and how a galaxy will experience bursts of new star formation or gradual declines, shaping its future for eons to come. Ultimately, research into stellar evolution is a key piece in the vast puzzle of cosmic evolution. By understanding how stars influence the fabric of galaxies, scientists can make educated predictions about the fate of not only our Milky Way, but also myriad other galaxies scattered across the universe. The story of stars is indeed the story of galaxies, revealing the intricate and interconnected nature of the cosmos. As humanity gazes into the cosmos, the dream of exploring and inhabiting other celestial bodies becomes increasingly possible through advanced technologies. One of the most promising avenues involves the development of advanced propulsion systems. Traditional rockets rely on chemical propulsion, which limits the speed and efficiency of space travel. Concepts such as ion propulsion and nuclear thermal propulsion could dramatically reduce travel time to distant destinations like Mars or even the moons of Jupiter and Saturn, enhancing the feasibility of sending humans to explore these worlds. Another vital area of innovation is life support systems, essential for sustaining human life in the harsh environment of space. Closed-loop life support systems could recycle air and water, making long-duration missions viable. We are already seeing prototypes of these systems being tested aboard the International Space Station. Additionally, the ability to grow food in space through hydroponics or aeroponics could address the nutritional needs of astronauts and future settlers, creating a sustainable food source far from Earth. Habitat construction technologies also play a critical role in making extraterrestrial living a reality. Innovations in 3D printing could enable humans to construct habitats using materials found on other planets, such as lunar regolith or Martian soil. This approach reduces the need to transport building materials from Earth, allowing for more efficient use of resources. Furthermore, inflatable habitats offer flexibility and ease of transport, expanding possibilities for creating living spaces on distant worlds. Lastly, technologies for energy production will be crucial for habitation beyond Earth. Solar panels could harness sunlight on celestial bodies with ample sunlight, like the Moon and Mars. In addition, nuclear reactors provide a reliable power source, supporting everything from life support systems to rovers and research equipment. As these advancements come to fruition, they will not only make exploration more feasible, but could set the stage for humanity's first steps towards becoming a multiplanetary species. Quantum entanglement is a fascinating phenomenon that reshapes our understanding of locality, which is the principle that objects are only directly influenced by their immediate surroundings. In a classical view, if two particles are separated by significant distances, any interaction between them should be limited to local effects. However, quantum entanglement defies this intuition. When two particles become entangled, the state of one particle is instantly correlated with the state of the other, no matter how far apart they are. This means that a change to one particle will instantaneously affect its partner, challenging the very fabric of classical physics. This instantaneous connection between entangled particles suggests that information can be shared over vast distances in ways that seem to defy the speed limit set by the speed of light. Albert Einstein famously dubbed this phenomenon spooky action at a distance, reflecting his skepticism about entanglement's implications. Despite Einstein's reservations, experiments have consistently confirmed that entangled particles do indeed exhibit this behavior, indicating that our universe doesn't strictly adhere to the classical laws of locality we once thought were absolute. The implications of quantum entanglement extend far beyond philosophical musings. They open doors to revolutionary technologies. For instance, quantum entanglement is the foundation for quantum computing, which has the potential to solve complex problems much faster than classical computers. Moreover, it paves the way for secure communication systems, such as quantum cryptography, which could create unbreakable encoding through entangled particles. In a world increasingly driven by information, these advancements promise to change how we process and protect data. As we continue to explore the mysteries of entanglement, we find ourselves standing at the intersection of science and philosophy. Our conception of reality is evolving, as entanglement suggests that the universe is more interconnected than we had previously imagined. It beckons us to reconsider the very principles that govern the cosmos, hinting at a richer, often stranger tapestry that lies beneath the surface of our everyday experiences. This shift in understanding not only enriches our scientific perspective, but also invites us to ponder our place within the vast, intricate universe. In the early universe, quantum fluctuations played a crucial role in shaping the cosmos as we know it. During the first moments after the Big Bang, the universe was an extremely hot and dense soup of energy and particles. In this chaotic environment, the laws of quantum mechanics came into play, allowing energy to appear and disappear in tiny amounts, a phenomenon known as quantum fluctuations. These fluctuations are not just random noise, they represent the very seeds of structure in the universe. As the universe expanded, it cooled down, and these minute fluctuations became stretched across vast distances by the rapid inflationary period that followed the Big Bang. This rapid expansion meant that tiny variations in energy density were magnified, eventually leading to the formation of galaxies and other structures. Essentially, quantum fluctuations served as the building blocks for the large-scale structure of the universe, allowing irregularities and differences to develop where matter would later accumulate. Moreover, these fluctuations are thought to contribute to the cosmic microwave background radiation that we observe today. This radiation is a remnant of the heat from the early universe, and the small variations in its temperature can be traced back to the quantum fluctuations that occurred during that incredibly early phase. Scientists study these variations to understand the origins of our universe and the forces that shaped its evolution. Quantum fluctuations provided the initial variations in energy that propelled the formation of structures in the universe. They underscore the intricate interplay between quantum mechanics and cosmology, illustrating how microscopic events in the infancy of the cosmos can lead to the vast and complex universe we see around us today. The connection between quantum physics and cosmology reveals the remarkable ways in which the fundamental laws of nature dictate the evolution of everything we observe. The observer effect in quantum mechanics is a fascinating concept that touches on the very nature of reality itself. At its core, it suggests that the act of observation can influence the behavior of quantum particles. In simple terms, when we measure or observe these tiny entities, their properties seem to change. This phenomenon can challenge our traditional understanding of reality, leading to differing interpretations of what it means for something to exist. One common example of the observer effect is the behavior of particles such as electrons. When they are not being observed, they can display characteristics of both particles and waves, existing in a state of probability. However, once we take a measurement, they seem to choose a specific state. This idea brings to light a critical question. Does reality exist independently of our observation, or is our perception integral to its existence? This philosophical inquiry underpins many of the interpretations of quantum mechanics. Different interpretations emerge from this foundational question. The Copenhagen interpretation suggests that physical systems don't have definite properties until they are measured. In contrast, the many worlds interpretation posits that all possible outcomes of a quantum event actually occur in parallel universes, thereby removing the significance of observation in determining outcomes. These debates illustrate how deeply quantum mechanics can influence our understanding of reality, blurring the lines between what is real and what is merely a product of observation. Ultimately, the observer effect invites us to rethink everything we know about reality. As scientists explore the quantum realm, we find that the universe may not be as straightforward as we once assumed. This intersection of science and philosophy not only illuminates the complexities of the quantum world, but also sparks curiosity about the very nature of existence itself. Each interpretation offers a glimpse into the enigmas of our universe, urging us to explore further into the strange and beautiful world of quantum mechanics. Quantum tunneling is a fascinating phenomenon where particles can pass through barriers that, according to classical physics, they shouldn't be able to overcome. This delicate dance of particles at the subatomic level opens a window into our understanding of astrophysics, where the sheer scale of the universe often interacts with the peculiar laws of quantum mechanics. Researchers have found that examining quantum tunneling can shed light on several cosmic processes that are otherwise puzzling. One significant area impacted by quantum tunneling is nuclear fusion within stars. In the incredibly hot and dense cores of these stellar giants, hydrogen atoms fuse to form helium, releasing enormous amounts of energy. Classical physics suggests that the electromagnetic repulsion between the positively charged protons would prevent them from getting close enough to fuse. However, quantum tunneling allows some protons to tunnel through the barrier, facilitating fusion even at lower temperatures than classical theory would predict. This insight not only helps explain stellar life cycles, but also informs our understanding of how stars like our Sun shine. Tunneling also plays a critical role in processes like the formation of supernovae and neutron stars. When a massive star exhausts its nuclear fuel, it collapses under its own gravity. Quantum tunneling is involved in the processes that lead to electron capture and neutronization in the core, events that are essential for creating heavier elements through explosive nucleosynthesis. By studying these quantum effects, astrophysicists can better understand the formation of elements that are scattered across the universe, contributing to the building blocks of planets and life itself. Furthermore, researchers explore quantum tunneling in the context of black holes and the early universe. Theories surrounding cosmic inflation, the rapid expansion of space immediately after the Big Bang, often invoke quantum mechanics to explain how tiny fluctuations could have led to the vast structure of the universe we see today. By delving into quantum tunneling, scientists continue to refine their models and deepen their understanding of the cosmos and its origins, revealing the intricate connections between the very small and the very large. This ongoing exploration highlights just how essential quantum mechanics is in painting the grand picture of our universe. Quantum mechanics is the branch of physics that delves into the behavior of the smallest particles in our universe. It offers a unique lens through which scientists can explore and understand the fundamental building blocks of matter. At a basic level, quantum mechanics reveals that particles exist in a state of probability rather than certainty, allowing researchers to manipulate and observe them in ways that classical physics cannot. One of the pivotal concepts from quantum mechanics is the idea of superposition, where particles can exist in multiple states simultaneously until they are measured. This principle is instrumental in high-energy particle physics experiments, such as those conducted at large particle colliders. When particles are smashed together at tremendous speeds, the conditions created can lead to the emergence of new particles that may have never been observed before. By analyzing these collisions through the framework of quantum mechanics, scientists can infer the presence of new forces or particles that could shape our understanding of the universe. Furthermore, quantum entanglement, the phenomenon where particles become interconnected and the state of one can instantaneously affect another, has implications for the search for new forces. This interconnectedness may hint at unseen dimensions or interactions that exist beyond the familiar four dimensions of spacetime. Researchers are now contemplating theories that expand our comprehension of gravity, electromagnetism, and even potential forces, which could ultimately lead to the discovery of new particles. The pursuit of understanding through quantum mechanics not only aims to uncover these new particles, but also to unite various physics theories into a more coherent framework. As scientists continue to unravel the mysteries of the quantum realm, we inch closer to answering profound questions about the very nature of our universe, its origins, and its future. Each step forward in quantum research illuminates possibilities that ignite the imaginations of physicists and cosmologists, propelling the quest for knowledge ever onward. Advancements in technology have profoundly transformed our ability to observe cosmic phenomena, offering us deeper insights into the universe than ever before. With the development of sophisticated telescopes, both on Earth and in space, astronomers can now detect light and other electromagnetic radiation emitted from distant stars and galaxies. These telescopes are equipped with highly sensitive sensors that can pick up faint signals, revealing objects that were previously invisible to the naked eye. One of the most significant breakthroughs comes from space observatories, like the Hubble Space Telescope. Launched in the early 1990s, Hubble has provided stunning images and a treasure trove of data that stretch our understanding of the cosmos. By sitting above Earth's atmosphere, it avoids the distortion caused by air turbulence, allowing for crystal-clear observations. This has led to discoveries such as the acceleration of the universe's expansion and the identification of exoplanets, worlds located outside our solar system. More recently, we have seen the rise of other innovative technologies, such as radio telescopes and gravitational wave detectors. The array of antennas used in radio astronomy can capture signals from the cold, dark corners of space, allowing scientists to explore phenomena like pulsars and cosmic background radiation. Observatories like the Laser Interferometer Gravitational Wave Observatory, on the other hand, have opened a new window into the universe, revealing cataclysmic events like black hole mergers and neutron star collisions through the ripples they create in space-time. These technological advancements not only enhance our ability to observe, but also democratize access to cosmic phenomena. With data being made available to researchers and enthusiasts alike, we are witnessing an unprecedented era of collaboration and discovery that continues to unveil the mysteries of the universe. Every step forward in technology brings us closer to answering the profound questions about our existence and the origins of the cosmos itself. Space telescopes, such as the Hubble Space Telescope, have dramatically transformed our understanding of deep space. Launched in 1990, Hubble was positioned high above the Earth's atmosphere, free from the blurring effects caused by atmospheric distortion. This unique vantage point allowed astronomers to capture notably clearer and more detailed images of celestial bodies, from distant galaxies to stellar nurseries and beyond. One of Hubble's most significant contributions has been its ability to probe the distant universe. By studying light from faraway galaxies, Hubble has helped determine the rate of expansion of the universe, a key factor in understanding its age and size. This work has led to the discovery of dark energy, a mysterious force responsible for the accelerating expansion of the universe. Such findings have opened new avenues of inquiry in cosmology and deepened our knowledge of fundamental cosmic phenomena. Moreover, Hubble has played a critical role in the study of star formation and the life cycle of galaxies. By observing various phases of stellar evolution, it has revealed insights into how stars are born, live, and ultimately die. Its observations of nebulae, vast clouds of gas and dust, have enriched our comprehension of the ingredients necessary for new star systems to form. Hubble's breathtaking images have not only expanded our scientific knowledge, but have also inspired public interest in space exploration. The vibrant colors and intricate structures portrayed in its images invite viewers to contemplate the vastness of the cosmos and our place within it. Each snapshot from Hubble serves as a reminder of the universe's incredible complexity and beauty, fueling curiosity and inquiry about what lies beyond our tiny planet. When astronomers observe distant supernovae, particularly a type known as Type Ia supernovae, they gain critical insights into the universe's expansion. These stellar explosions occur in binary systems, where one star is a white dwarf. When the white dwarf accumulates enough mass from its companion star, it undergoes a dramatic collapse and explodes. This type of explosion is extremely bright and consistent in its luminosity, making it an excellent standard candle for measuring astronomical distances. By observing the brightness of these supernovae, scientists can determine how far away they are. When they compare this distance with the redshift of the light, an effect caused by the expansion of the universe, they gather valuable information about the rate at which the universe is stretching. The redshift indicates how much the wavelengths of light have been stretched as the universe expands, allowing researchers to see how fast objects are moving away from us. Interestingly, as astronomers collected data from these distant supernovae, they made a surprising discovery. Instead of slowing down, the universe's expansion is actually accelerating. This revelation led to the hypothesis of dark energy, a mysterious force that counteracts gravity and is thought to be driving this acceleration. These findings have reshaped our understanding of cosmology and the fundamental forces at play in the universe. Each distant supernova serves as a cosmic beacon, guiding scientists in measuring the universe's expansion. The intricate relationship between distance and redshift has opened up new avenues of research and deepened our understanding of the universe's past, present, and future. With every observation, we edge closer to unlocking the secrets of the cosmos, revealing a universe that is ever expanding and full of surprises. The James Webb Space Telescope, often referred to as JWST, marks a remarkable leap forward in our quest to understand the universe. Launched in December 2021, this impressive observatory is designed to see farther into space and deeper into time than any of its predecessors. Its advanced technology allows it to observe celestial phenomena in infrared light, offering a view of the cosmos that is shrouded in dust and gas. This ability will enable scientists to study the formation of stars, galaxies, and planetary systems in unprecedented detail. One of the most exciting aspects of JWST is its potential to uncover the mysteries surrounding the first stars and galaxies that formed after the Big Bang. By measuring the faint light from these ancient cosmic entities, researchers hope to gain insights into how they evolved over billions of years. This could answer fundamental questions about the nature of the universe and the processes that led to the formation of the complex structures we see today, including our own Milky Way galaxy. In addition to exploring the distant universe, the James Webb Space Telescope is equipped to investigate planets outside our solar system, known as exoplanets. By analyzing their atmospheres, JWST can detect the presence of elements like water, carbon dioxide, and even potential signatures of life. This capability opens up new avenues for understanding not just how other worlds form, but also the conditions that might support life beyond our planet. The significance of the James Webb Space Telescope extends beyond its technical prowess. It symbolizes humanity's enduring curiosity and our quest to grasp the vastness of the cosmos. With each discovery, JWST has the potential to rewrite our understanding of astrophysics, sparking new questions and inspiring future generations of scientists. As it takes us further into the universe's depths, we stand on the brink of remarkable revelations about the past, present, and perhaps the future of our existence among the stars. Astronomers face a unique set of challenges when interpreting data from extraterrestrial telescopes, which are instruments placed in space to observe celestial phenomena. One primary concern is the sheer volume of data collected. Space telescopes like the Hubble and James Webb gather vast amounts of information across various wavelengths. Sifting through this data to find meaningful patterns often requires immense computational power and sophisticated processing algorithms. This means that a significant amount of time can be spent simply organizing the data before analysis can begin. Another crucial challenge is the calibration of the instruments themselves. Unlike ground-based telescopes, which can more easily be adjusted or repaired, space telescopes operate in the harsh environment of outer space. Factors like temperature fluctuations, cosmic radiation, and even micrometeoroid impacts can affect the instrument's sensitivity and accuracy. Ensuring that the data is correctly calibrated so that it reflects true astronomical events is essential for any effective interpretation. This requires meticulous work and often involves complex models to predict and compensate for these environmental effects. Additionally, astronomers must grapple with the limitations of our understanding of the universe. Many celestial objects behave in ways that challenge our existing theories. Newly discovered phenomena may require revisiting established concepts in cosmology or astrophysics. For instance, the identification of exoplanets reveals not just about their composition, but raises questions about their atmospheres and potential for life. Each discovery often leads scientists down new paths of inquiry that require further study and sometimes even new technology to investigate. Finally, collaboration plays a fundamental role in tackling these challenges. Interpreting data is not a solitary endeavor. Astronomers often work in multidisciplinary teams that include physicists, engineers, and data scientists. Sharing insights and pooling expertise can illuminate the complexities of the data being analyzed. The collaborative effort enriches our understanding and helps to unravel the mysteries of the cosmos, ensuring that even the challenges presented by extraterrestrial telescopes can lead to profound discoveries about the universe we inhabit. The formation of our solar system, a vast and intricate story that began around 4.5 billion years ago, is filled with fascinating mysteries that scientists are still unraveling today. At its core, this tale starts with a massive cloud of gas and dust known as a solar nebula. When parts of this cloud collapsed under its own gravity, it eventually led to the birth of the Sun at its center, surrounded by a swirling disk of material. But questions still linger about how the planets, moons, asteroids, and comets formed from that initial material. One of the biggest mysteries revolves around why our solar system has such a distinct arrangement of planets. The inner planets, Mercury, Venus, Earth, and Mars, are rocky and smaller, whereas the outer planets, Jupiter, Saturn, Uranus, and Neptune, are larger and gas giants. Scientists are exploring a variety of theories, including the role of temperature differences in the protoplanetary disk. These variations may have influenced where and how different materials could condense, leading to the diverse types of planets we see today. Another enigma concerns the presence of water and other volatiles on Earth and the outer planets. How did these essential elements make their way to the inner planets, particularly our own? One hypothesis suggests that icy bodies like comets and asteroids delivered water to the inner solar system after the planets were formed. But the timeline of these deliveries and the chemistry involved are still subjects of significant research and debate. Lastly, there's the mystery of the so-called Planet 9, an elusive entity theorized to exist beyond Neptune. Astronomers have noted strange orbits of distant objects in the Kuiper Belt that suggest the gravitational influence of an unseen planet. Whether this great mystery represents an unknown planet or a group of smaller bodies remains to be seen. With each new discovery, our understanding of the solar system's formation deepens, reminding us that the cosmos is full of profound questions just waiting to be explored. The environments of Venus and Mars serve as remarkable examples of how different conditions can shape planetary evolution in unique ways. Venus, often called Earth's twin due to their similar size and composition, has undergone a vastly different trajectory. With its thick atmosphere, composed mainly of carbon dioxide, Venus experiences an extreme greenhouse effect that raises surface temperatures to around 800 degrees Fahrenheit. This oppressive heat, combined with crushing atmospheric pressure, creates a world hostile to life as we know it. The geological features of Venus, such as its vast plains and volcanic structures, suggest a complex history, possibly including volcanic activity that has contributed to its current state. In contrast, the environment of Mars presents a much cooler and drier landscape. Once thought to be similar to Earth, Mars has since revealed extensive evidence of past water flows, with river valleys and lake beds suggesting a much wetter climate in its ancient past. The thin atmosphere of Mars, mainly carbon dioxide but lacking in significant pressure, cannot support liquid water on its surface for long. Instead, any water present quickly evaporates or freezes. The exploration of Mars has unveiled intriguing challenges to the notion of habitability, as scientists study how its climate shifted from a potentially life-friendly planet to the barren environment we see today. These planetary environments underline the concept of planetary evolution driven by a range of factors, including distance from the Sun, atmospheric composition, and geological activity. For Venus, proximity to the Sun likely resulted in its harsh conditions, while Mars, being farther out, faced different evolutionary challenges. Both planets illustrate the variations in planetary processes and highlight the delicate balance of factors that can support or inhibit life. Moreover, studying the differences between these two planets provides invaluable insights into the history of our solar system and informs our understanding of exoplanets orbiting distant stars. As we continue to explore, these contrasting environments might help us identify potential biosignatures and climates that are conducive to life beyond Earth. Each planet tells a story, a tale of evolution influenced by myriad physical and chemical processes, revealing the diversity of planetary environments in our cosmic neighborhood. Comets and asteroids are like time capsules from the early solar system, offering invaluable insights into its formation and evolution. When the solar system was born around 4.6 billion years ago, it was a chaotic environment, filled with gas, dust, and a variety of small rocky and icy bodies. Comets and asteroids are remnants of that primordial material. Studying them helps scientists understand what the building blocks of the planets were and the conditions that existed during their formation. Asteroids are primarily found in the asteroid belt between Mars and Jupiter. They represent the rocky leftovers from the formation of the inner planets. By analyzing the compositions of various asteroids, researchers can determine the types of materials present when the planets were forming. Some asteroids contain minerals and organic compounds, hinting at processes that were happening when our solar system was still in its infancy. For example, certain carbon-rich asteroids may provide clues about the ingredients necessary for life. Comets, on the other hand, are icy bodies that come from the colder regions of the solar system, particularly from the Kuiper Belt and the Oort cloud, which lies far beyond Neptune. When a comet approaches the Sun, it heats up and releases gas and dust, creating a spectacular tail. These outbursts allow astronomers to study the volatile compounds and basic building blocks of water and organic molecules that comets carry. This is particularly fascinating as it raises questions about the origins of Earth's water and the fundamental ingredients for life. Together, these celestial bodies not only contribute to our understanding of the early solar system, but also reveal how planetary systems can evolve over time. Through ongoing missions to explore asteroids and comets, scientists continue to uncover the mysteries of our cosmic neighborhood, piecing together the story of our solar system's past and its potential for supporting life. Each discovery reminds us of the dynamic and ancient history that predates our planet and could inform us about the conditions necessary for life elsewhere in the universe. The study of exoplanets, or planets outside our solar system, has profoundly reshaped our understanding of the cosmos and our place within it. Just a few decades ago, the idea of planets orbiting stars beyond our sun was mainly relegated to science fiction. Today, we know of thousands of exoplanets, each revealing diverse characteristics that challenge our prior notions of what a planet can be. This wealth of discovery has prompted scientists to reassess the dynamics of our own solar system, leading to some illuminating insights. One fascinating realization is the variety of planetary systems that exist out there. Many exoplanets are found in configurations that are quite different from our own. For instance, some orbit their stars in close proximity, leading to extreme climates and unlikely environments for life as we know it. Others exist in systems with multiple planets orbiting in close quarters, creating a dance of gravitational influences that we do not observe in our solar system. This has led scientists to consider whether our solar system is a typical case or an anomaly in the vast array of planetary architectures. Moreover, the discovery of exoplanets has spurred discussions about the formation and evolution of planetary systems. By studying the characteristics of these distant worlds, researchers can piece together insights about processes involving dust and gas in young star systems, ultimately showing how they evolve over time. The evidence indicates that planets can form in a multitude of ways, challenging previous models that did not account for the wide array of planetary types now observed. Finally, the search for potentially habitable exoplanets has invigorated our quest for understanding life's origins. Finding Earth-like planets has encouraged scientists to study environmental conditions in our own solar system, focusing on whether planets like Mars or moons like Europa could harbor life. In this sense, the study of exoplanets not only expands our cosmic horizons, but also refines our understanding of where we fit in, invigorating the age-old question of whether we are alone in the universe. The gas giants, which include Jupiter, Saturn, Uranus, and Neptune, hold a unique place in the study of planetary formation due to their size, composition, and the role they play in our solar system's architecture. Unlike terrestrial planets, which are smaller and rocky, gas giants are predominantly made up of hydrogen and helium, with deep atmospheres and massive cores. Their formation mechanisms provide critical insights into how different types of planets develop under varying conditions. One significant aspect of gas giants is their ability to attract and retain large amounts of gas and dust from the protoplanetary disk early in the solar system's history. This accumulation is crucial because it hints at how planets can grow and vary in size based on their distance from the Sun and the available materials. For instance, Jupiter's immense gravity allowed it to capture much more gas than smaller planets like Earth, which affects their current atmospheres and potential habitability. Furthermore, studying the gas giants reveals insights into the migration of planets. Research has shown that early gas giants may have shifted significantly from their original positions due to gravitational interactions. This migration could explain the current arrangement of the planets in our solar system and gives us clues about the dynamics in other planetary systems across the galaxy. In addition, gas giants often have intricate systems of moons and rings, which provide a laboratory for studying the processes of formation and evolution in different environments. Examining these structures enhances our understanding of not only these massive planets, but also the diverse characteristics that can exist in planetary systems. This makes gas giants crucial not just for theorizing about our own solar system, but also for examining planetary formations beyond it. Physicists often face the challenge of studying phenomena that are not directly observable, like black holes or dark matter. In these cases, they rely on indirect evidence to build their theories. This process involves using data collected from observations of related phenomena, experiments, and statistical analysis. For instance, while we cannot see black holes directly, we can observe their effects on nearby stars and gas. By studying the movements and behaviors of these objects, physicists can infer the presence and properties of the unseen black holes. One of the most powerful tools in this indirect evidence approach is the use of models. These are theoretical frameworks that describe how we expect the universe to behave based on known laws of physics. When experiments or observations reveal discrepancies between expected and actual results, these models can be adjusted or expanded. For example, the discovery of cosmic microwave background radiation provided significant indirect evidence for the Big Bang theory, reinforcing our understanding of the universe's beginnings. Additionally, mathematicians play a crucial role in formulating these theories. They develop equations that describe relationships between measurable quantities, allowing physicists to make predictions about unobservable phenomena. An excellent example of this is the way scientists study gravitational waves. These ripples in space-time, predicted by Einstein's theory of general relativity, were not observed until years of research and indirect measurements. The eventual detection confirmed the theory and expanded our knowledge about the cosmos. Ultimately, the interplay between observation, mathematical modeling, and theoretical predictions not only allows physicists to speculate about the unobservable, but also pushes the boundaries of our understanding. By piecing together these clues, much like detectives solving a mystery, scientists continue to unveil the secrets of the universe, bridging the gap between the seen and the unseen. Computer simulation has become an essential tool in modern astrophysical research, providing scientists with a way to explore cosmic phenomena that are often beyond the reach of direct observation. Many of the processes that occur in the vastness of space, such as the formation of galaxies, the evolution of stars, and the behavior of black holes, are complex and can be difficult to study through traditional methods. Simulations allow researchers to create virtual models of these processes, replicating the laws of physics and enabling them to predict outcomes based on varying conditions. One of the most significant contributions of computer simulations lies in their ability to visualize and analyze vast amounts of data. By inputting different parameters, scientists can modify the conditions of their models to see how different factors influence cosmic events. For instance, when studying the formation of a galaxy, simulations can incorporate variables such as the gravitational pull of dark matter, gas dynamics, and star formation rates. As a result, researchers can observe the evolution of galaxies over billions of years within a fraction of actual time. These simulations also enhance our understanding of phenomena that we may not be able to witness directly. Consider black holes, which can't be observed through visible light. By simulating their gravitational interactions and the effects they have on nearby matter, scientists can gain insights into their behavior and properties, contributing to our understanding of fundamental theories like general relativity. Moreover, simulations play a key role in predicting future astronomical events and guiding observational campaigns. They provide a framework for scientists to anticipate where and when to focus telescopes in search of new discoveries. The interplay of computer simulations and observational astronomy is a hallmark of modern astrophysical research. As technology advances, simulations become increasingly sophisticated, allowing scientists to incorporate more variables and achieve greater accuracy. This synergy not only expands our knowledge of the universe, but also sparks new questions and lines of inquiry in the ever-evolving field of astrophysics. Without computer simulations, our grasp of the cosmos would be significantly less profound. The quest to unite general relativity with quantum mechanics has captivated scientists for decades. General relativity, developed by Albert Einstein, elegantly describes the force of gravity as the curvature of space and time around mass. This theory beautifully explains the large-scale structure of the universe from planets to galaxies, yet it does not account for the peculiar behavior of matter and energy at the tiniest scales, where quantum mechanics reigns supreme. Quantum mechanics, on the other hand, governs the behavior of particles, forces, and energy that exist at microscopic levels. The challenge arises because the two theories operate on fundamentally different principles. General relativity is deterministic and smooth, while quantum mechanics introduces randomness and uncertainty. To reconcile these vastly different frameworks, scientists are exploring various theoretical approaches to quantum gravity. One prominent idea is string theory, which proposes that the basic building blocks of the universe are not point particles but rather tiny vibrating strings. These strings can create different particles and fundamental forces, potentially providing a unifying framework that includes both gravity and quantum mechanics. Another intriguing approach is loop quantum gravity, which seeks to quantize space-time itself. Rather than starting with particles and forces, this theory suggests that space is made up of tiny, discrete loops woven into the fabric of the universe. This perspective implies that space can be divided only down to a certain limit, challenging our conventional understanding of a smooth continuum and offering insights into the conditions that existed at the birth of the universe. Both of these theories, along with others being developed, aim to offer a deeper understanding of black holes, the early universe, and the fundamental nature of reality itself. While the path to a complete theory of quantum gravity remains uncertain, the exploration itself enriches our comprehension of the cosmos, inviting us to ponder the profound connections that exist in the fabric of space, time, and everything within it. As scientists continue to probe these enigmatic realms, each discovery brings us one step closer to understanding the universe in its entirety. In recent years, several breakthroughs in astronomy have sparked new debates and questions concerning established theories of our universe. One striking example involves the observation of gravitational waves. First detected in 2015, these ripples in spacetime provided strong confirmation of Einstein's theories of relativity. However, subsequent discoveries have revealed even more complex phenomena that challenge our understanding of black holes and the nature of gravity itself, suggesting that there is still much we need to learn about these enigmatic cosmic objects. Another fascinating development concerns the acceleration of the universe's expansion. Initially, it was thought that the expansion would slow down due to gravitational forces, yet measurements from distant supernovae and cosmic microwave background radiation revealed that the universe's expansion is actually speeding up. This surprise led to the concept of dark energy, a mysterious force driving this acceleration. Researchers are still grappling with the exact nature of dark energy, leading to numerous models and theories that vie for clarity and acceptance. Furthermore, the study of exoplanets, planets beyond our solar system, has taken a remarkable leap forward. With advanced telescopes like the Transiting Exoplanet Survey Satellite, or TESS, scientists have discovered thousands of these distant worlds. Some of them reside in the so-called habitable zones, where conditions might be right for life. This raises important questions about life's prevalence in the universe and whether our existing theories about planet formation and habitability adequately account for such diverse environments. Lastly, the development of new imaging technologies, particularly with the Event Horizon Telescope capturing the first-ever image of a black hole's shadow, has reverberated through the scientific community. Such technologies have empowered astronomers to test long-held beliefs about black hole formation and behavior. These breakthroughs illustrate the dynamic nature of astronomy, reminding us that each discovery can open the door to more questions, challenging our understanding of the cosmos and our place in it. Interdisciplinary approaches play a crucial role in unraveling the mysteries of the universe. By drawing knowledge from various fields such as physics, astronomy, biology, and even art, researchers can examine cosmic phenomena from multiple perspectives. This collective wisdom allows scientists to forge connections that may not be immediately obvious when viewed through the lens of a single discipline. For instance, the interplay between physics and biology encourages explorations of how life might exist in extreme environments beyond Earth. Take, for example, the collaboration between astronomers and computer scientists. High-tech simulations powered by advanced algorithms can help visualize complex cosmic events, making them easier to comprehend. These visual representations allow researchers to test theories about the formation of galaxies or the dynamics of black holes, advancing our understanding of the universe's evolution. Meanwhile, philosophers contemplating the implications of these discoveries encourage meaningful dialogue around the nature of existence itself, bridging the gap between the empirical and the abstract. Moreover, the intersection of chemistry and astrophysics has opened doors to studying the composition of celestial bodies. By analyzing the chemical signatures from distant stars and planets, scientists can discern their potential for hosting life and understand their origin. This synergy not only enriches our comprehension of the cosmos, but also fuels curiosity about our place within it. Each discipline adds a layer of richness, empowering researchers to create a more holistic narrative about the universe. Ultimately, embracing an interdisciplinary mindset can lead to breakthroughs that single-discipline studies might overlook. As we explore the cosmos, the blend of diverse fields ignites imagination and fuels inquiry. In doing so, it reveals a universe that is as intricate as it is beautiful, inviting us to dig deeper into its profound mysteries. Throughout human history, the universe has served as a profound source of inspiration for artists and creators. From the earliest cave paintings that depicted celestial bodies to contemporary works embracing the vastness of space, the cosmos has shaped our imagination and creativity. Ancient civilizations looked to the night sky, observing stars and planets, which not only guided their agricultural practices, but also found their way into myths and legends, illustrating humanity's strong connection to the universe. During the Renaissance, artists like Leonardo da Vinci began to incorporate elements of science into their work, marrying artistic expression with the pursuit of knowledge. The awe-inspiring discoveries of this era, such as the heliocentric model proposed by Copernicus, encouraged artists to explore the themes of cosmic order and human existence within the vast universe. This period birthed masterpieces that conveyed the wonder of the stars, utilizing perspective and light to represent the infinite. As we moved into the Romantic period, artists began to explore the sublime nature of the cosmos. Painters like Caspar David Friedrich used the backdrop of the night sky to evoke emotions of transcendence and the beauty of nature. This era also saw the emergence of literature inspired by the stars, with poets and writers reflecting on humanity's place in a seemingly infinite expanse, grappling with both the beauty and the mystery of existence. Today, modern artists and filmmakers continue to draw upon the universe's grandeur. Whether it's through stunning imagery of distant galaxies in films or public art installations that incorporate astronomy, the cosmos remains a fountain of inspiration. As we uncover more about the universe through science and technology, our artistic expressions evolve, reflecting our ongoing quest to understand our place in this vast, mysterious universe. Throughout history, the cosmos has captivated the imaginations of writers and filmmakers alike, leading to a rich tapestry of literature and cinema that explores themes of space, time, and humanity's place in the universe. One of the most notable works is Arthur C. Clarke's novel 2001, A Space Odyssey. Published in tandem with Stanley Kubrick's film of the same name, this story delves into the evolution of humanity, artificial intelligence, and the mysteries of monoliths that guide human destiny, encapsulating the awe and wonder of space exploration. Then there's the celebrated novel Contact by Carl Sagan, which beautifully intertwines science and philosophy. Its protagonist, Dr. Ellie Arroway, discovers a signal from an extraterrestrial civilization. The narrative raises profound questions about the universe, humanity's search for significance, and the possibility of a broader collective existence beyond Earth. Sagan's ability to communicate complex scientific concepts with elegance makes this work a standout in nurturing a love for the cosmos among readers. On the cinematic front, films like Interstellar, directed by Christopher Nolan, tackle the themes of time dilation, black holes, and human survival. The narrative not only takes viewers on a visually stunning journey through space, but also explores the emotional ties that bind us, emphasizing love as a powerful force transcending even time and distance. This blend of scientific rigor with human emotion creates a profound connection with audiences. Another iconic entry is the timeless science fiction series The Twilight Zone, created by Rod Serling. Through its anthology format, the series frequently incorporated cosmic themes, exploring alternate realities, the unknown, and moral dilemmas against vast, otherworldly backdrops. Each episode invites viewers to ponder our existence, often leaving them with more questions than answers, perfectly encapsulating the mysterious nature of the universe and our place within it. Ancient astronomy has profoundly shaped how we interpret the universe today. Civilizations like the Babylonians, Greeks, and Mayans observed the night sky meticulously, linking their findings to mythology, agriculture, and navigation. Their interpretations often involved storytelling, weaving cosmic events into the fabric of cultural narratives. For instance, constellations were personified in stories that explained creation, seasonal changes, and moral lessons, creating a rich tapestry of understanding that still resonates in various cultures. As we advanced in scientific knowledge, many concepts from ancient astronomy persisted in our language and thought processes. Terms like retrograde to describe the apparent backward motion of planets stem from old descriptions. Such linguistic remnants remind us that our predecessors, though not scientists by today's standards, were making sense of the universe as best as they could, often with remarkable accuracy. They recognized patterns and cycles in celestial phenomena that are still relevant in modern astronomy. Moreover, the philosophies born from ancient astronomical observations influence contemporary spiritual and cultural viewpoints. Many indigenous cultures continue to honor celestial cycles, viewing them through a lens of respect and integration with the Earth. This perspective fosters a deep connection between the cosmos and human experience, emphasizing harmony with nature rather than viewing ourselves as isolated observers. Such ideas encourage modern societies to rethink their relationship with the universe and their place within it. Lastly, the pursuit of knowledge sparked by ancient astronomers feeds into our current fascination with the cosmos. As we gaze up at the stars today, we stand on the shoulders of those early stargazers. Their inquiries laid the groundwork for our scientific explorations, reminding us that understanding the universe is as much about answering questions as it is about appreciating the beauty and mystery of existence itself. Ancient observations not only help shape scientific terms and methods, but also foster a cultural legacy that continues to inspire wonder and curiosity. Myths and legends have long served as powerful tools for understanding our place in the universe. From the ancient civilizations that gazed at the night sky, the stories they crafted provided explanations for celestial phenomena that were otherwise mysterious and awe-inspiring. For instance, the Greeks told tales of gods and goddesses represented by constellations, turning the heavens into a canvas of human narratives that blended the divine with the natural world. These myths not only offered comfort in the face of life's uncertainties, but also fostered a sense of community as they were shared and passed down through generations. As societies evolved, so did their cosmological stories. Native American tribes, for example, wove their cultural beliefs into the stars and moon, seeing them as spiritual beings and guides. The Milky Way was often referred to as a pathway or river that connected the Earth to the cosmos, reinforcing the idea of a relationship between humans and the heavens. These legends instilled a sense of stewardship and respect for the universe, as well as a deeper connection to the land and the cycles of nature. They urged societies to observe the stars not just as distant lights, but as integral parts of their existence and identity. In modern times, while we have gained scientific understanding of the cosmos through telescopes and space missions, the allure of mythical narratives remains potent. Today's storytelling often merges scientific inquiry with metaphorical themes, as we explore concepts like black holes and the potential for extraterrestrial life. Popular media, such as films and literature, continue to use mythic structures to interpret human experiences and aspirations, illustrating our endless quest to uncover the universe's mysteries. Ultimately, myths and legends teach us that our journey through the cosmos is not just a scientific endeavor, but a deeply human one. They remind us that as we seek to explore and comprehend the vastness of space, our imaginations and stories are as essential as the calculations and observations of scientists. Through these narratives, we find commonality in our curiosity, fear, and wonder, forging a shared connection across cultures and time as we gaze up at the stars. Scientific discoveries about the universe significantly shape contemporary philosophical debates, prompting us to rethink ideas central to our understanding of existence, reality, and ourselves. For instance, the revelation that our universe is vast and constantly expanding challenges the traditional view of a static cosmos. This shift encourages philosophers to explore our place in an ever-changing universe, raising questions about the nature of time, causality, and the idea of infinity. Moreover, the discoveries about black holes and the possibility of multiple universes have direct implications for discussions about determinism and free will. If our universe is just one of potentially countless others, what does that mean for the choices we perceive as ours? This idea can lead to debates about the meaning of our actions and the nature of reality itself. Are we merely part of a grand cosmic experiment, or is our existence more meaningful in the context of a single universe? Philosophers also grapple with the implications of cosmic discoveries for ethics and morality. For instance, the understanding of our Earth as a small, fragile oasis in a vast universe has inspired many to consider our responsibilities toward the planet and one another. It prompts us to ask difficult questions about stewardship, the value of life, and how we prioritize our actions. This ecological perspective can reshape ethical frameworks, pushing for a more inclusive view that considers not only humanity, but all living beings and future generations. Finally, the intersection of science and philosophy unveils the potential for dialogue between the two fields. Philosophers examine the implications of scientific theories, while scientists can draw inspiration from philosophical questions. This interplay enriches our understanding of both the universe and ourselves, revealing that the search for knowledge is as much about inquiry as it is about wonder. It suggests that while scientific discoveries push the boundaries of what we know, they also deepen our engagement with the questions that define our existence. The concept of time in cosmology is a fascinating and complex subject that intertwines with our understanding of the universe. In the context of cosmological models, time is often perceived as a dimension, just like the dimensions of space. Just as we move through space, we also move through time. This framework stems from Einstein's theory of relativity, which revolutionized our understanding by suggesting that time is not an absolute constant. Instead, it can vary depending on speed and gravity. In the vast, expanding cosmos, time plays a crucial role in the evolution of the universe itself. For instance, in the Big Bang model, time began as the universe rapidly expanded from an incredibly hot and dense state about 13 billion years ago. In this scenario, the flow of time is intimately linked to the expansion of space. As galaxies move apart, the passage of time takes on new meanings, prompting questions about the relationship between time and the physical laws governing cosmic phenomena. Moreover, time is not truly uniform throughout the universe. Clocks in stronger gravitational fields or those moving at extraordinary speeds tick at different rates than those in weaker fields or at rest. This leads to fascinating implications, such as the observation that time runs slightly slower for astronauts on the International Space Station compared to those on Earth. These differences highlight the interconnectedness of space, time, and gravity, reshaping how we perceive our own timelines in relation to the wider cosmos. Ultimately, the nature of time in cosmological models invites us to reflect on profound philosophical questions. What does the future hold as the universe continues to expand? Will time behave differently in distant eras? These inquiries not only push the boundaries of science, but also tap into our deep-seated desire to uncover the mysteries of existence, reminding us that time itself is a vital key to understanding the universe. Defining the edge of the universe is quite a fascinating challenge. In our modern understanding, the universe doesn't have an edge in the sense that we might imagine, like the boundary of a vast ocean. Instead, the universe is often described as expanding, with galaxies moving away from each other. This expansion means that the observable universe, which is the part of the universe we can see and study, is defined by the distance light has traveled since the beginning of time, approximately 13.8 billion years ago. This gives us a measurable limit to what we can observe. Beyond this observable universe lies what we often call the unobservable universe. Current theories suggest that the universe likely extends far beyond our visible limits. This part is shaped by the same physical laws and possibly contains more galaxies, stars, and planets that we simply cannot see. It raises intriguing questions about the nature of reality itself. If we consider the universe to be infinite, then there may not actually be a true edge at all. Rather, it could stretch on forever, beyond what we can measure or perceive. As for what lies beyond the boundaries we know, theories in cosmology venture into speculative territories. Some scientists entertain the idea of a multiverse, wherein our universe is just one of many. Each could have its own set of physical laws and constants, creating a rich tapestry of realities beyond our own. This concept pushes the limits of our imagination and challenges our understanding of existence itself. Ultimately, the quest to understand the universe and its boundaries reflects one of humanity's oldest desires, to comprehend our place in the cosmos. Even though many questions remain unanswered, each discovery brings us closer to unveiling the mysteries of what lies beyond our observable horizon, igniting curiosity and wonder in all who ponder these grand questions. The concept of infinity is one of the most profound and perplexing ideas in cosmology. When we think about the universe, we often envision it as vast and boundless, stretching out far beyond what we can see. Infinity suggests that not only does the universe go on forever, but that it may also contain an infinite number of stars, galaxies, and other celestial bodies. This realization challenges our ability to fully comprehend the scale and nature of everything around us. One major complication that infinity introduces is the question of how we measure and compare the vastness of space. In our everyday lives, we use finite numbers to make sense of quantities. For instance, we might say there are several million stars in a galaxy. However, when we suggest that the universe could host an infinite number of galaxies, it becomes difficult to wrap our minds around what that means. How do we conceptualize something that has no limits? This abstraction pushes the boundaries of human understanding and humbles our place within the cosmos. Furthermore, infinity has implications for theories about the universe's origin and fate. Cosmologists grapple with questions such as whether the universe has always existed or if there was a beginning. If the universe is infinite, it raises paradoxes about time. If it had to start sometime, what does that mean for infinite space? Equally compelling is the notion of a multiverse, which suggests that our universe could be just one of countless others, each potentially different yet equally infinite in its expanse. The concept of infinity forces us to reconsider the nature of reality itself. It confronts us with limits of perception and comprehension, encouraging scientists and thinkers alike to delve deeper into the mysteries of existence. While infinity may complicate our understanding, it simultaneously inspires a sense of awe, reminding us of how much there is yet to discover in the universe. The laws of physics play a crucial role in shaping the universe and its myriad celestial bodies. These laws, rooted in fundamental principles like gravity, motion, and thermodynamics, dictate how stars, planets, and galaxies form and evolve over time. For instance, gravity acts as the architect of the cosmos, pulling matter together and enabling the formation of everything from the smallest asteroids to massive clusters of galaxies. This attraction between particles creates dense regions in space that eventually collapse to form stars and planets. As stars form, they go through various stages of nuclear fusion, converting hydrogen into helium and releasing energy. This process not only gives stars their luminosity, but it also influences their mass and eventual life cycle. The balance between the outward force of this energy and the inward pull of gravity is a delicate dance that determines whether a star will swell into a red giant or explode as a supernova at the end of its life. Such explosive events play a vital role in disseminating elements throughout the universe, contributing to the formation of new stars and planets in a cyclical process known as stellar nucleosynthesis. The behavior of celestial bodies is also governed by the laws of motion. Newton's laws of motion and gravitation explain how planets orbit stars and how moons orbit planets. These laws predict the paths of celestial bodies with remarkable accuracy, allowing scientists to calculate trajectories for spacecraft and understand phenomena like tidal forces, which arise from the gravitational pull of the moon on Earth. The interaction of these forces creates complex systems, such as the rings of Saturn or the intricate dance of moons around Jupiter, making our solar system a fascinating realm of study. In addition to gravity and motion, thermodynamics plays a significant role in celestial behavior. The temperature and pressure within stars influence their life cycles, while in space, the second law of thermodynamics explains the inevitable trend toward increased entropy. This governs everything from the cooling of planets to the formation of black holes, where regions of space become so dense and gravitationally attractive that not even light can escape. Through these interconnected principles, the laws of physics provide a framework that shapes the cosmos, allowing us to understand the formation, evolution, and behavior of celestial bodies across the universe. The journey of our understanding of gravity began thousands of years ago, with early thinkers like Aristotle believing that heavier objects fall faster than lighter ones. It wasn't until Sir Isaac Newton in the 17th century that a profound shift occurred. Newton proposed his famous law of universal gravitation, which described gravity not just as a force between objects, but a force that acts at a distance, connecting everything from an apple falling from a tree to the motion of the moon around the Earth. This breakthrough laid the groundwork for classical mechanics, providing a clear framework for how we perceive gravitational interactions. In the early 20th century, Albert Einstein revolutionized our comprehension of gravity further with his theory of general relativity. He showed that gravity is not merely a force but a curvature of space-time caused by mass. This concept suggested that massive objects like planets and stars bend the fabric of the universe around them, creating pathways for other objects to follow. This theory elegantly explained not only why planets orbit the Sun, but also predicted phenomena like the bending of light around massive bodies, which has since been confirmed through observation. Despite these significant advancements, several fundamental questions about gravity remain unanswered. For instance, while we understand gravity's effects on large scales, its behavior at the quantum level is still shrouded in mystery. This brings us to the complexities of black holes, where the rules of general relativity clash with quantum mechanics. The nature of gravity inside these enigmatic regions of space has sparked ongoing research, with scientists eager to develop a unified theory that encompasses both quantum mechanics and general relativity. Additionally, the discovery of dark matter and dark energy has introduced new variants into our questions about gravity. These substances seem to dominate the universe's mass-energy content, yet remain elusive, not interacting with light or known forms of matter as we understand them. As researchers continue to probe the depths of space and delve into the fundamental forces of nature, our understanding of gravity evolves, encouraging us to seek answers to these profound and captivating questions. The search continues, reflecting our innate curiosity about the universe and our place within it. Advancements in computational power have revolutionized our understanding of the universe through more intricate and detailed astrophysical simulations. Just a few decades ago, simulating celestial events required vast amounts of time and minimal complexity due to the limitations of technology. Today, however, supercomputers can process immense data sets, allowing scientists to create sophisticated models that can mimic the behavior of galaxies, stars, and even black holes. These powerful simulations enable researchers to predict a variety of phenomena, from the formation of cosmic structures to the intricate dance of gravitational interactions. For instance, scientists can now explore how galaxies collide and merge, revealing insights into their evolution. With increased computational capacity, it is even possible to simulate events like supernova explosions, which are crucial for understanding the life cycle of stars and the synthesis of elements in the universe. Moreover, enhanced computational abilities have facilitated the incorporation of complex physical processes. This includes factors such as dark matter dynamics, the impact of cosmic rays, and the behavior of gases under extreme conditions. As we refine our models and increase fidelity, the accuracy of our predictions improves, leading to a deeper comprehension of the cosmos. Ultimately, the interplay between technology and astrophysics reshapes not only our theoretical frameworks, but also our observational strategies. Improved simulations guide where we should focus our telescopes and resources, making the journey into understanding the universe more precise and exciting than ever before. The deeper we delve into these simulations, the closer we come to unraveling the mysteries of our universe. Artificial intelligence, often referred to as AI, has become an indispensable tool in the realm of cosmic data analysis. Its role is crucial because the universe generates staggering amounts of data, far beyond what a human could process effectively. From galaxies flung across vast distances to the faint whispers of cosmic microwave background radiation, AI helps scientists sift through this complexity, finding patterns and signals that may otherwise remain unnoticed. One of the remarkable applications of AI in cosmology is its ability to classify and interpret various celestial phenomena. For example, consider the discovery of new exoplanets. Traditional methods require intricate calculations and substantial time. AI algorithms can analyze light signals from distant stars, detecting subtle dips that indicate a planet's transit. This process significantly accelerates our understanding of potentially habitable worlds outside our solar system. Moreover, AI is highly adept at managing data from astronomical surveys. Observatories like the Vera C. Rubin Observatory will generate enormous datasets as they scan the night sky. AI assists in automating the detection of transient events, such as supernovae or gravitational waves, by rapidly analyzing images and identifying anomalies. This efficiency not only enhances our observational capabilities, but also increases the chances of catching fleeting cosmic events in real time. Overall, the intersection of artificial intelligence and cosmic exploration opens new frontiers in our understanding of the universe. By harnessing the power of AI, scientists can uncover deeper insights into the workings of galaxies, stars, and fundamental questions about the nature of existence itself. As we continue to advance technologically, the collaboration between human intellect and artificial intelligence promises to illuminate even darker corners of our cosmic landscape. As we look to the future of space exploration, emerging technologies hold the promise of unlocking the secrets of the universe, even in the most distant corners of space. One of the most exciting avenues is the advancement of increasingly sensitive telescopes. These instruments will likely be equipped with enhanced detectors that can capture faint light from stars and galaxies billions of light-years away. With bigger mirrors and improved optics, future telescopes could dramatically increase our ability to observe the cosmos in unprecedented detail. Another area of progress lies in the development of new spacecraft propulsion systems. Traditional rocket technology limits the distances we can travel within our solar system. However, concepts like ion propulsion and solar sails could enable spacecraft to travel much farther and faster. Imagine a mission that takes us to the outer reaches of our solar system or even interstellar space, gathering data from environments that were once thought to be beyond our reach. These missions could yield insights about the early solar system and even exoplanets in distant star systems. Moreover, advancements in artificial intelligence and machine learning will revolutionize data analysis. With the vast amounts of data that telescopes and sensors will gather, algorithms can help sift through this information more efficiently than any human team could manage. This means we can discover patterns, identify celestial phenomena, and analyze complex data sets much faster, leading to new discoveries and a deeper understanding of cosmic events. Finally, the growth of collaborative ventures in space exploration, like international partnerships and private space companies, will further enhance our capabilities. By pooling resources, knowledge, and technology, we can launch more ambitious missions and reach beyond what any single organization could achieve alone. The future of space exploration is not just about the technologies we know today, but about the innovations on the horizon that promise to expand our understanding of the universe in ways we have yet to imagine. As humanity eyes the stars, questions about the ethical implications of exploring and colonizing other planets come to the forefront. In our quest to reach celestial bodies, we must contemplate the potential consequences of our actions, not only on those planets, but also on ourselves. One of the primary ethical considerations involves the preservation of extraterrestrial ecosystems. Just as we recognize the importance of conserving our own planet's biodiversity, we must ask ourselves whether we have the right to disturb or exploit ecosystems we do not yet fully understand. Another vital consideration is the potential for contamination. When sending missions to other planets, particularly those that may harbor life, there is a risk of introducing Earth life forms that could disrupt or endanger native organisms. This concern raises questions about the moral responsibility we bear to protect these alien environments from harm. The principle of planetary protection guides many current space missions, underscoring our obligation to minimize human impact on the cosmos. Moreover, the prospect of colonizing other worlds brings up moral and social implications. If we establish settlements on other planets, Who gets to control these new territories? Historically, the colonization of lands on Earth has often resulted in abuse, exploitation, and conflict. It is crucial that we learn from our past and ensure that any endeavors in space respect the rights of potential future inhabitants and avoid replicating the injustices of history. Lastly, we must reflect on the motivations behind our cosmic ambitions. Are we driven by a genuine desire to explore and extend human knowledge, or is it a quest for resources and expansion? Understanding our intentions is essential to shaping a future in space that prioritizes ethical considerations, balances exploration with responsibility, and fosters a sense of stewardship for our universe. Before we take those monumental steps beyond our blue planet, these questions must guide our journey forward. The quest to understand our universe has far-reaching implications that go beyond mere curiosity. This pursuit fosters technological innovation on Earth, as scientists and researchers tackle the monumental challenges that come with studying vast cosmic phenomena. When we look at the ambitious projects aimed at unraveling the secrets of space, such as telescopes observing distant galaxies or spacecraft exploring other planets, we also witness the birth of new technologies that often find applications in our daily lives. For instance, the development of powerful telescopes requires advancements in imaging technology, which eventually contributes to improvements in various fields like medicine and telecommunications. Devices such as high-resolution cameras and sensors used in medical imaging, like X-rays and MRIs, trace their lineage back to technologies originally developed for astronomical research. This shows a direct line of influence where challenges in understanding the cosmos inspire breakthroughs that enhance life on Earth. Moreover, the rigorous demands of space exploration lead to innovations in materials science. The need for lightweight, durable materials that can withstand extreme temperatures and pressures in space has resulted in developments that improve everything from transportation systems to consumer electronics. These innovations not only push the boundaries of what is possible in space, but also create a ripple effect across various industries, enhancing efficiencies and altering how we live and work on our planet. The endeavor to decode the mysteries of the universe serves as a catalyst for human ingenuity. As we venture further into the cosmos, the technologies that emerge from this exploration reshape our world, often in unexpected and transformative ways. Each discovery paves the path for the next, driving a cycle of innovation that inspires us to dream even bigger and continue reaching for the stars.